Welcome to the Beijing and Singapore MariaDB Server Fest 2020. Huanying Lai Dao MariaDB Server Fest. Earlier this week we have had two MariaDB Server Fests, one in Paris for Europe, Middle East and Africa, and one in New York for the Americas. Now we're happy to be in Beijing and Singapore for our users in the Asia Pacific region. I'm looking forward to 3 days devoted to the users of MariaDB Server, the open source relational database management system, a fundamental building block of the Internet of modern applications, on-prem and in the cloud. The conference is hosted by the MariaDB Foundation, a non-profit that promotes the openness and adoption of MariaDB Server. This is the moment that we've been waiting for. It feels good to stand here in front of a big crowd. Well, that's what I would say at a face-to-face conference. Now I'm sitting in front of my laptop in Grankulla, Finland, but I am still excited. I'm excited to work on the adoption of MariaDB Server with you, the DBAs, DevOps and developers of applications based on MariaDB. In our previous unconferences, we've been working on code contributions from those developing MariaDB Server itself at IBM, Microsoft, Alibaba, Tencent and our other sponsors on top of the MariaDB Corporation roadmap. So this is a virtual conference and we have had a couple of innovations for you based on attending our other virtual conferences the last month. First, we have the conference 3 times in 3 time zones so that you can attend it daytime. We have material for 2 long days, but we decided to spread it out over 3 days so you can get other things done. Second, we have pre-recorded the presentations. This makes timing easier and hopefully sound quality better. And it makes subtitles possible, which should simplify understanding of both native and non-native accents. Third, and most importantly, interactivity over Zulip chat and WeChat. The presenter is available with full attention to take questions throughout the presentation. So for Zulip, go to mariadb.org/zulipfest. It should be less than a minute to set up a chat account and then join the MariaDB Server Fest stream. The stream is separated into 1 topic per presentation, so you can chat freely on 1 topic even if the next presentation begins. Now, why do we have this conference a 3rd time this week in Beijing and Singapore? Well, there are several reasons. First, we want to interact with you in your time zone during your daytime. Now, we and the presenters are available to chat with you, not too early morning, not too late night. Second, we have some presentations that are especially interesting in your region, submitted by MariaDB users from China. And third, we want to use the tools that you normally use, also in China. So we're also broadcasting on Bilibili and we're also chatting on WeChat. This is in addition to YouTube and Zulip chat. But let's now take a look at today's program. So the first one is Dulipa Vijayawardena and Victor Dupshabakka from Supermetrics, who are users. That's what you can see in the yellow colored presentations on mariadb.org/fest2020/schedule. They're talking about Supermetrics and the many bears, a modern-day fable on the search for the perfect database. Then we have Tera Ju, how to help financial customers use Tencent Cloud MariaDB. After that we have Li Peng, a user story migrating from Oracle to MariaDB. Then we go to a RED presentation where RED stands for hardware. It's Krunal Bauskar, MariaDB on R. Then we go to a feature set presentation. Those are in blue in the schedule. Richard Bensley, SQL Mode Ludicrous, a collection of interesting and productive special features that he has encountered in his many years of using MariaDB. Then we have Yang Chen looking at the MariaDB usage at bilibili.com. After that, it's our chairman of the MariaDB Foundation, Eric Herman, who is comparing ecosystems between MariaDB Foundation and the Foundation for Public Code. And the day is concluded by two blue presentations. First one by Vincenzo Ciorbaru, who's talking about the S3 storage engine, long-term archival with MariaDB's S3 storage engine. And then we have Sergei Petrunia talking about the optimizer trace, walking through its features and users. So let's get going with day one. So now for our first set of presenters, Gulipa Vijayawardana and Victor Djupshebaka with Supermetrics and the Many Bears, a modern-day fable on the search for the perfect database.
Welcome to Supermetrics and the Many Bears, a modern-day fable about searching for the perfect database. So this presentation from us is kind of a bit weird to do, right, Victor?
Yeah, COVID and all that.
Yeah, I mean, normally we'd be in front of you in an audience, you'd be looking at us, you'd be waving at us, you'd be giving us questions and things like that. We can't do that. We kind of broke into our actual office and are presenting this to you together so that we can have a conversation with you about looking for the perfect database in our organization and some of the stories and the problems we had. And we'd love for you to ask questions of us afterwards so that you get the most out of this. But certainly we decided that the story format was better than trying to have lots of screens. So the deck itself is fairly short, but the conversation we're going to have is going to be much longer. And obviously it is a bit strange talking at our computer screens rather than to you all. So if we stumble, we'll probably pick each other up and go on from there. So first of all, I'd like to introduce myself. My name is Dupes. I have a very long name. I'm a software and data geek, and I started out started out a very long time ago, but I worked for a company called Bioware, and then from there to MySQL and Sun. And then I started my own startup, Empire Avenue. And then somewhere along the journey, I discovered this incredible startup that our CEO, Mikael, had started and joined the company about 3 years ago here in Finland. So we are presenting this to you, the depth of the night in Helsinki, Finland.
My name is Victor. I also have a background as an entrepreneur and a software developer. And I've been at Supermetrics for about 4 years now. And the hair has grown about the same pace as the company, as you can see from the old photo.
And actually, when I started, we were about 9 or 10 people. You had just started 3 months before that. And now we're in 3 countries and 120 people and an amazing growth story and one of Finland's incredible growth startups, if not one of the fastest growing companies in the Nordics. So with that being said, Victor, why don't you give us some information about Supermetrics?
Yeah, so a quick intro to what we do. Basically, we bring data from one place to another, and that sounds very, very simple, right?
Extremely simple.
But the reality is not that simple. It's a lot more complex than that. We integrate with over 60 different platforms. We call them data sources. So mostly in marketing, but also from basically any area. we fetch data from these data sources, process them in our backend, store some data in different types of databases, and push the data out aggregated to different types of tools where our customers do reporting. So typical use case is the spreadsheet tools, Google Sheets and Microsoft Excel, very popular. Data visualization tools, but also data warehouses, especially for the bigger enterprise customers.
Now, you said store data, but in most cases, do we actually store data or?
Yeah, well, a lot of the processing does happen in real time. So we do store some data, but that's mostly for caching. So it's the typical situations we fetch most of the data actually from the data source in real time. And that brings some interesting challenges.
So you can see some of the numbers there. There's like terabytes of data being transferred, millions, hundreds of millions of queries, or 75 plus million queries, and something called 3 billion query seconds. What is a query second, Victor?
By query second, we mean a query being processed on a server for 1 second.
Right. So what does that query processing look like?
So here's a simplified overview of what our application looks like. It's a pretty standard setup, actually. We have requests coming in. We put them in a queue. We have workers picking up jobs from the queue. We go to the data sources to fetch the data, and we store that, as I said, in different types of databases, depending on the use cases. And we'll dive more into those different types of databases in a while.
Right, and of course, when we talk about storing, we're always talking about caching in many cases. But of course, we have some data sources where we have to store the data for a longer term cache or a longer term amount of time.
Yeah. So, for example, in some cases, the data source APIs don't provide the type of reporting APIs that we need to gather the data in real time. So in that case, we basically need to fetch raw data from the data sources, store it somewhere, and do the aggregation on our end.
Right. And so the interesting thing about talking about this application is that, I mean, there's a pretty standard stack, as you saw, like a pretty standard tech stack of workers working on things, processing data. I mean, obviously, we can't get into the secret sauce of how all that happens, but in terms of applications, it's not that unusual. And that's actually one of the interesting things about this application is that we have many different types of use cases that we have to deal with. But I think if you want to look at our application as a kind of a mental picture, you could look at it from the perspective of Finland itself. So this is a beautiful country, and I hope after coronavirus is done with and COVID-19 is gone, you get a chance to come here to Finland and visit and come to our office and say hi to us, certainly. But we have in Finland we have something like 30 million lakes. I heard something like that, like a few lakes.
Maybe,
per
but that sounds a bit much. But
okay, so
definitely more than 1,000.
Oh, definitely more than 1,000. Okay, so I think it's like in the 30,000s, 100,000. I don't know, but it's a lot of lakes in this country. It's beautiful, and of course, water flows from lake to lake, from river to river. And if you think about data as that water that is flowing across all these lakes and rivers through an application, then wherever data starts to collect, then it becomes a pool of water. Something that you have to dive into, you have to dissect, you have to figure out what's in there. And these pools of data become larger and larger in an application, and then they become a lake. And we all know that trying to cross a calm lake is better than crossing a stormy one. Victor has to deal with a lot of stormy lakes when it comes to databases. So our landscape is filled with these kind of pools. And one of the interesting things, and we don't get into this in this presentation, is that when you look at any technology stack, we tend to look at data structures or databases, and these are from vendors like MariaDB or Google BigQuery or wherever. But wherever you have a bunch of data, that is in itself a database and can become a problem for us. And that could be a queue system. So just keep that in mind as we go through this, because it kind of feeds into all the different types of databases that we have. Now, we structured this presentation as a fable, and the fable that we chose was Goldilocks and the Three Bears, because the three bears were testing out all the different beds to figure out which one was the perfect bed.
Wasn't it Goldilocks who tested the beds?
I believe so. Actually, you're right.
But anyway.
But that's because the bears were sleeping in different types of beds.
Exactly.
Exactly. All right. So, fables aside, so where does Mama Bear sleep?
Mama Bear is the traditional relational database. So in our use case, this means a lot of MariaDB, it means some Aurora MySQL, and it means Google Cloud SQL. We're a hybrid cloud, so we use multiple cloud vendors and different solutions there.
So what's Mama Bear looking for, Victor?
Well, it's a typical startup scenario, right? You start with a small application, you build a proof of concept. Especially back in the days, the obvious choice for data storage was the relational database. And that's where it all began for Supermetrics as well. But we still use a lot of relational databases, and MariaDB in particular. And the strength there is obviously the ability to do table joins. There's the indexing, which we use very, very much to have performant queries. But apart from that, we don't actually use the more advanced features of relational databases that much, like procedures or triggers or similar.
And that's an interesting thing about us, actually. We use relational databases, but we don't necessarily use all the features inside of a relational database. But transactional, ACID-compliant data is very important to us.
That's obviously very important, yes, for the core application data.
But relational databases have had a problem with us as well.
Yes. As I mentioned, started out small, yes, that's fine, a couple of hundreds rows, maybe a few thousands of rows. But then the business grows, suddenly there's millions of rows, we add new features, joining tables, can be dozens of millions of rows. We do a lot of inserts, we do a lot of updates, a lot of deletes.
Lots of replicas.
Lots of replicas. And especially traditionally, the use cases or the type of things that we did wasn't necessarily optimized for relational databases. So other types of database solutions might have been better options there.
And of course, other problems with relational databases for Supermetrics has also been we may have databases in different parts of the world. They're not necessarily distributed, and it's hard to deal with multi-master systems and things like that. So management of those kind of systems can be a problem. And then if we go into some of the vendor locked-in solutions, such as AWS Aurora or Cloud Spanner, then, well, we're vendor lock-in.
Hard to be hybrid cloud then.
Yes, hard to be hybrid cloud, and you end up optimizing for each of the cloud vendors that you have, which isn't necessarily where we want to be as a company. So
that's Mama Bear in a nutshell. What's Daddy Bear then?
Oh, Daddy Bear. Daddy Bear's a simple kind of guy. He doesn't like this SQL stuff. and he thinks that we should just be able to get the data out of the thing. So Daddy Bear for us is Redis Enterprise, which is the enterprise commercial version of Redis that you get on open source. And I'll explain a little bit more about that later. We have Elasticsearch, and believe it or not, we have. I'm going to consider Daddy Bear to also be our file systems as well. So
you're kidding, right?
Come on. Hey, you know the system as well as I do. So yes, EFS and Google Cloud Storage. Yeah, like I said, Daddy Bear is a bit simple. So yeah. So what's Daddy Bear looking for? Well, like I said, he's simple. He's not looking for relational data. It's NoSQL data, non-relational, very much key value systems or document-based systems. We're looking at documents or data sets that are 10 bytes to hundreds of megabytes or more in our case. Now, each of the three main areas there, or four things there, kind of have a different use case for us. So, for example, Redis is very much our short-term caching solution in memory as much as possible. Then we have Elasticsearch is actually our metadata layer that we query for our logs and some analysis. And then we have our file systems. And the file systems is, well, there was a reason why we ended up in the file system. And that was because we were trying to store huge amounts of data into Redis. And I don't mean transactions into Redis. I mean like hundreds of megabytes of data into Redis, which...
Hundreds of gigabytes.
Hundreds of gigabytes. Wow, what's a meg? What's a gig? It all comes down to the same thing, right? So end up, we couldn't do that. But we needed to get this data back out. And so we decided to put it into file systems. It actually worked out really well, which is amazing. But of course, the speed is variable. Networking, file I/O, different cloud vendors.
Yep.
Yeah. But
it has its purpose for very big files.
Indeed. And we discovered the efficacy of that. Now, one of the I mentioned Redis Enterprise is because we moved from Redis open source to Redis Enterprise because there's a lot of things that gives us. And then there's a story about all of this that comes back to MariaDB at the end of this. So Redis Enterprise gives us the ability to use SSD storage instead of memory so for large files. And this can be very useful in sub-second queries that we need to do. So, but we wanted to share some of our war stories, and one of the war stories actually was fairly recent, and I'm going to mention a few names in our company, Nicholas and Method. They had to mostly deal with this. In their situation, they were dealing with a data source where we did need to store the data. This wasn't a real-time data. We needed to fetch the data for customers. And when we initially did our tests and did the scoping and the specs, we found that it was small bits of data. We could throw it into Redis. I think that was
the natural solution for
absolutely
key value store.
Key value store. It makes perfect sense. In memory, we're going to do that. And suddenly we were doing a test run with actually, I don't think it was just a handful of customers. And suddenly that data set wasn't the 5, 10 megs that we were talking about, actually turned into the 50, 100, 150 megs, which...
Gigs again,
megs, gigs, you know what I'm talking about. And that can be a bit of a problem when it comes to memory and cost. And it strikes at the heart of a CTO's heart here. So what do we do? What did we do? Well, we had to think about it again, and we had to go from a non-relational database to a relational database. We actually had to rethink how the application was working. And this comes down to one of the problems with non-relational NoSQL data structures is that your application has to deal with that. And in our kind of analytical aggregated, where we're looking at data aggregations, sometimes that is actually not the best way to deal with it. And there is a good reason why SQL was created, and you kind of walk right back. So what did we end up with? We ended up with, in this situation, moving from non-relational to relational.
Back to MariaDB.
Back to MariaDB. Actually, we actually walked right back to MariaDB, which was entertaining in that we discovered a lot of ways of improving even that solution as well. So, with that being said, however, next up is
Baby Bear, last but not least. And here we're talking about the data warehouse type of storage. So in our case, a lot of Google BigQuery, but also Snowflake and PrestoDB. And if you're not familiar with Snowflake and PrestoDB, Snowflake is a vendor that provides a data warehouse solution that works across clouds. So at least in Google Cloud, AWS and Azure, whereas PrestoDB is an open source file-based
columnar stored database.
Originally developed by Facebook.
Right.
But yeah, it's Baby Bear, but not a very tiny Baby Bear. So we're talking very, very big data here. But the key is that, for us at least, is that we're able to do able to use SQL. Mm-hmm. So we can do table joins, and we can still query a lot of data really fast as long as we do proper database structuring.
But it's not really suited for anything small, right?
Right. There's always a cost to everything, and in this case, both storage and querying can be quite expensive depending on the use case. So it's not the ultimate solution to every use case.
And of course, for us, BigQuery and Snowflake, these are potentially internal databases that we use for internal analytics and things like that. But for one of our scale cases, we ended up going with PrestoDB. And what was the use case there?
Yeah, so there the interesting case was blackout.
And this is what happens when we do this very late at night, kids. No, in this case, we were taking data initially into MariaDB.
Right, so we're working with MariaDB and hit the limits there. The queries were just too massive for MariaDB to handle. And at that point, I think it was Andy, our head of data engineering, who came up with the suggestion that, hey, let's try PrestoDB. It could be a better fit for this particular purpose.
And it was, from a cost perspective, from a ease of use perspective. I mean, we now query gigs. I think we actually query a terabyte of data in there somewhere, and has been quite effective for us. But of course it has its downsides. It is file-based. It does have limitations in changing table structures and things like that. It's
updating data is not really an option.
Exactly.
It's only inserting and deleting.
So there's lots of issues with each of these particular things. But
an interesting point here as well is that we actually use Redis as well.
Oh, right, of course. We couldn't actually just do it just against Presto.
Yeah, so to insert row by row or even like hundreds or a few thousands of row at a time wasn't really an option. We needed to first gather bigger data sets and then push them all, push all the rows at once. So we actually used Redis there for the gathering of data.
And that brings us to whether Goldilocks. See, I did get the fable right? Okay, see?
Eventually, yes.
Eventually, right. So did Goldilocks find their perfect bed? So let me ask a question before we get into this slide and talk about this, Victor. How do we actually get our data into Elasticsearch, by the way, for our logs?
Yeah, so we push our logs from application level, but we definitely do not push them directly to Elasticsearch.
Oh, whoa. Why not? I mean, come on. It should be able to handle this.
Yeah, but then if Elasticsearch goes down for some reason...
Has that ever happened? Really?
Nah.
No,
Really.
No.
Then suddenly we're out of logs, and the logs are very important for us, so we can't let that happen. So again, we use Redis as an kind of intermediary storage there.
Well, I think this is the kind of the moral of the story, though, in the end, right? So in everything that we talked about, I think this is where we also... So here... so with some stories that we've talked about going from relational to non-relational. But in a lot of cases where we have actually gone from non-relational back to relational, as I've said in the stories, and part of that is we keep coming back to SQL. We keep coming back to the ease that we have with working with SQL, and it's like putting in an old coat. And you just feel comfortable in it, and it's easy to get going. So MariaDB and MySQL has been a constant feature in our lives. I don't think it's ever gone away, and in fact, we're expanding our use.
Yeah.
But more often than not, we end up with
one form of hybrid solution. That's usually where we get the most performance and the most cost effectiveness and so on.
So, and that's an interesting thing. It's like, so we kind of look at our data structure or the database for a specific part of our application, not as one database, but as a hybrid database. One cannot exist without the other. It's not saying that, we can just live with one. And sometimes it's three.
Yeah, it can even be all three of them. So, for example, having the final ultimate set of data in the data warehouse, storing part of it in a traditional relational database like MariaDB, and then maybe some aggregated data or very often used data in Redis for the more key value type caching.
And maybe that's the perfect solution. Do you think that there is possibly somewhere out there a perfect solution that we still haven't tried, or that we can use for our scale, like something that is globally distributed, data warehouse, columnar, maybe, or something like that, with a relational database as well, and some document or non-relational stuff, but also non-vendor lock-in across all our hybrid clouds solution. And what am I missing here? Oh, something in memory so that we can use it for key value as well. Like,
it sounds like a dream.
It is a dream. One that, I know there's a lot of people who've tried this, but yes.
To be honest, I don't know the answer to your question, but I certainly do hope that there is or will be. We've been following the developments of SkySQL with a lot of excitement, partly because of the multi-cloud and inter-cloud capabilities that you mentioned. We do use 2, if not 3 clouds, and we need to be able to have the data travel between these clouds. And if we do it ourselves, it means a lot of self-managed databases and a lot of maintenance associated with that. And
we don't have a lot of DBAs, though there might be someone watching that might want to come work for us, right? I mean, there's all sorts of cool things to do here, but I interrupted you, sorry. Yeah, but no, we don't have like dedicated DBAs, at least not at this point in time. So one option is to utilize the very best knowledge and experience that there is out there
in the form of Sky DBAs, and that's essentially a model that we have tried already with Redis Labs, as you mentioned, in the case of Redis. So using the enterprise solution for that.
And I think Supermetrics is an interesting use case. I think it's something, and I'll be honest, when I started here, my first thought was, this is going to be simple. We're going to use MySQL, as we already have, MariaDB, of course, plus Redis. Everything's going to be simple. But in actual fact, as we have scaled and as we have grown, we have so many different use cases that like nothing works just as you would like in one single database. And that seems to be the crux of the matter. They always say use the best tool for the job.
Exactly.
And that is true. We can't seem to use the best tool for the job. We have to use the best 3 tools for the same job to do the same query. It is not a joke to say that our application sometimes in one code piece might query the Redis, the relational MariaDB, and the data warehouse type structure within a 20-line span, and combine those 3 things together to give back the data set that we need. And that's a unique point, I think, in some cases.
Yeah.
So.
Yeah, and that's something where, as I said, we're excited about the potential of SkySQL and also the hybrid aspect that SkySQL provides.
But the other moral of the story is, of course, is how important relational databases have become, even though we thought that NoSQL, SQL battles would be waging even now, and our lives would be more NoSQL than SQL. So
we still find ourselves doing a lot of table joins.
Yes, we do. Yes, we do. But hey, one of the interesting things, and I think time is getting pretty short here for us. So we do want to say that Victor and I are basically like the messengers of an amazing team at Supermetrics. And I would be remiss to say that even these 5 names on this list, on this slide, is just the tip of the iceberg. Our thanks to Andy, Dimitri, Nicholas, Metod, Mikhail, and lots of other people. So, and by the way, I just want to put a plug in for Supermetrics and say that we are hiring, so please do check our jobs, but there may even be jobs that we haven't posted, so please do get in touch with us. Thank you very much to MariaDB Server Fest, to Anna, to Kai, to all the wonderful people there. Thank you for having us. It is very strange giving this presentation from this format. Victor and I, you and I have had a lot of fun trying to set this up today.
Very fun.
So we hope you'll come visit us here in Finland, and looking forward to the questions, and we'll answer as best as we can. It was a pleasure, and see you next time.
Our next presenter is Tera Zhou, how to help financial customers use Tencent Cloud MariaDB.
It's my honor here today to take part in the MariaDB Server Fest online conference. Before we talk about our topic, first let me introduce myself. I'm the product manager of a Tencent Cloud database team, and I once was a developer and for 7 years, and then I became a product manager for 5 years. So I've done this job for 12 years. Today we're going to talk about how to help financial users to use Tencent Cloud MariaDB. I think we there have 3 aspects to talk about. First is why we choose MariaDB, and I think this problem maybe can stem from why we choose it before we start up Tencent Cloud. Before we provide the database on the cloud, we actually use MariaDB for our account information, and then we provided the database to our customers in Tencent Cloud, and they have some requirements. We will talk about what we do to satisfy their requirements, and meanwhile how to enhance MariaDB. Okay. Why we choose MariaDB? I think there are nearly 4 reasons why we choose MariaDB. First one is new features, not just MariaDB 10.5, 10.4, but at the very beginning MariaDB have some features that MySQL don't have it, or they have it, but just in the enterprise version, such as the thread pool and some grammar, or in the native version we have S3 compatibility, but MySQL don't have it. Maybe it will have it later or never. Another one, MySQL don't have some engines that we have it in MariaDB, such as MyWorks or Column Store, and some other engines such as Cassandra. So we like it. Use MariaDB for some new features and some engines that will never happen in MySQL. And some other reason, maybe it's not some technical reason, but it's also very important. And sometimes that will make users to choose which one will be their best choice. First is the license. MySQL, there's some of their drivers under LGPL, and MySQL is under a commercial database company. Maybe there has some potential risk for us. So I think every user and every cloud provider have to consider it. And another one is open. Me and my colleagues have participated in several MariaDB conference. We've seen the decisions can be reviewed and debated, and we can talk about what we're going to do in the next version, and we can talk it with the developer, with Monty, so we like it. Okay, the last one. But we put the database on our public cloud and private cloud. We have more and more users, and especially the financial users. They have a lot of requirements, such as security. We have users from bank, from insurance company, from securities company, and they care so much about their security, not just themselves, but their supervision organization, some bureau, or some other organization from their industry, and they have a lot of data, and the data will accumulate from year to year, and we need to scale out the data, and we need to update the database without interruption, and they usually have one active node and two standby nodes, and also have some disaster recovery nodes from 1,000 kilometers away, and they need to have a high availability, more than 99.99%, and they would like to use some window function, some CETS, such as the grammar in Oracle. So there are a lot of requirements. We will do our best to satisfy them. We need to first look at our architecture of the database. Here you can see there is a meta cluster. The meta cluster stores all the information from the proxy, from the instance, from the agent, from the phase conversion, and from some other component. And here is the OS. The OS provides the APIs for the Red Rabbit Manager, and then users can use the Red Rabbit Manager to see how many instances here, what's the status of the instance, and what's the IP and port, and how about the status of the instance. And also we have a schedule manager, and the schedule manager will use the metadata to decide which one is alive and which route is right, or which proxy is right, and how to get rid of a node. And also we have some code backup center, a message center, and here is the LB. If we provide this in private cloud, this LB maybe it's hardware or LVS. When it's in public cloud, it's a component in the public cloud, so we call it VPC gateway. Okay, the first one we want to talk about is security here, the security. Okay, and there are three phases when we talk about the security. The first one is before the SQL come to the engine. We can see the connection here, so we need to encrypt the connection, have some authentication, and when the SQL come to the kernel, we have a kernel level security policy or SQL firewall. Here we can see in the proxy we can configure the SQL firewall, and maybe we have another misoperation prevention here to get rid of some bad happen. And after that we have the audit. Okay, here we can see the audit. First, the user needs to have some audit rows. We can have a regular expression, what SQL we include or not include, what SQL we equal or not equal client IP or execution time or users. And then we combine this row to our instance. And when this audit row happens, what we do to let it go or have a non-message for users, and then we get a audit log and see, so we can check a log and we can have some analyze for the log. Okay, another one is high availability. We talk about this. Users have more than 99.99% requirement for the availability. Here we can see another number here, 1, 2, 3, or 5, 6, 7. I'm going to talk about what's that mean. Okay, for the one step, the active database is downgraded to the standby. Maybe it's because some bad happened. You can see here we have active, and every active and standby means a process. This is MySQL or now MariaDB process, and every process have an agent. You know, here the agent gets a lot of information from the process, and we put all the information to the metadata. You know, remember to talk about it. To the metadata cluster, and the schedule load the data, and they know what happened to the master, to the active. So in the first step, the active database is downgraded to the standby. maybe it called down or something bad happened, and then in the second step, the standby report is the latest binary log location, and when they report the location, the schedule know which one is the latest location, and then the standby merchants can participate in the election, and then in the fourth step we reconstruct the master and the slave, and we modify the routing rule, and then the request from the proxy can directly to the new node from this one, and to the new node. And the entire switch process is fully automatic without human intervention. And so the strict handover process, we use this to ensure the data consistency. Okay, and another one. You can see this one high availability is happened just in one data center. But if we have more than one data center, so we need to have some other ways to fix that. In this example, we have 3 data centers, 1, 2, 3. And the active and this standby is in data center 1, and this standby is in data center 2. And in this data center, we don't have a standby, but we have a schedule node. We have a meta cluster node here. So when this data center have some network problem, but this data center don't know it, and so this data center don't know what happened in this data center. Maybe it's a network between the 2 data centers interrupt, or all this data center is fail over. So we need to use the schedule with the schedule all across the 3 data center to judge what happened, and we use this to avoid the split brain problem. Okay, if the network between the data center 1 and data center 2 is break, and we know because we have data center 3, so we can't connect to this data center, this schedule, but we have this and this, so we know what happened to data center 1. Then we get rid of this schedule node, and then we can have user data from their client to this data center. But of course, this maybe can't keep the consistency of data, but it can give a high availability. Okay, the fully replication. We will talk about this. Users of, the financial users like fully replication, because they want to keep the data between the standby and the active node is the same, so they can read the standby or read the data from the active node. Maybe that will affect the performance, but they can accept it. But for the full replication, before we did this work, MySQL don't have the fully synchronous replication, but now they have it. They have it in MySQL 5.7, and but still we have some advantages here. We have our asynchronous threads group. In MySQL, with fully synchronous replication, when a source commits a transaction, all replications must also have committed the transaction before the source return to the session that perform the transaction. Fully synchronous replication means failover from source to any replication is possible at any time. But the drawback of fully replication is that there might be a lot of delay to complete a transaction. So we do a little work here. We have a asynchronous thread here. That means in this place here in number 1, in MySQL, they just put the date to the binary and the data here from the step 2 and to the running log, or apply to the file, and then this thread just here to wait until there is ACK come back to the thread. But here we have a threads group. The thread just send the data to the standby. It's not a semi-synchronous. We just we use this thread to do some other work. But when this come back, when this ACK come back from the standby and the thread gets the ACK, and it will be wake up and to send the data back to the user. So the thread here is always doing the work, but not like MySQL to wait until the ACK come back. So it will always work. This is what we do for the fully replication. We call this asynchronous thread group. Okay. Another one is multi-source synchronize. This is used for our insurance company. We have, a lot of insurance company have some subsidiaries. These subsidiaries maybe use their database is totally different from their head office. Their head office maybe have use MariaDB or MySQL, but the subsidiary use Oracle, MariaDB, Postgres, MySQL, not the database. So they need to compile this data to their head office to do some analyze work. So we use the binary log extraction, and we pass the binary log, have the materialize the view log from the Oracle and put all the data to Kafka, and then there are some consumers put the data to MariaDB and or to some other databases. This is what we do for the multi-source synchronize, and then we have for data verification. We to keep the data right. Okay. Another one is DB Brain. We have DB Brain for MariaDB and some other database in private cloud and public cloud. There have monitoring information and before and provision components, and analyze or help user to analyze the database, to analyze the performance and maybe the data log, and also have some alarm message for users. And also we have some tools for users to fix the problem and have some emergency response components. And also we have a optimization report for users to modify their schema, modify their index, and something like that. And we have more than 70 monitor information, and have 5 graded monitor information, and we have audit. We talked about this before, and we have performance check program and security threat and alarm message, and we help users to queue session and help users to optimize their index, have some expert advice. Okay, user cases. This is your case from bank. Here in this bank, they have 3 regions. The first one is Shenzhen, another one is Shanghai. Shenzhen is the head office of Tencent. This bank has 3 data center, and the 2 data center is in Shenzhen, and another data center is in Shanghai. They have 1 master and 2 slaves in Shenzhen, but these 2 slaves just in another data center, and they use fully replication here. And also this master have a read-only node, and their clients read the data from the read-only or the master, and the slave here can't read any data from here. But if some field happens, they can switch from the master to the slave. And here we can see in Shanghai it have a asynchronous replication between the slave and this master. So use this asynchronous to keep the performance, and we here use the fully replication to keep the consistency of the data. And here we can see Shanghai and Shenzhen, we have a long distance. This means this 2 node actually is a disaster recovery node. This is what this bank deployment. Okay, thank you.
The next presenter is from China, Li Shunpeng, a user story migrating from Oracle to MariaDB.
Hello everyone, my name is Li Xunpeng from MariaDB Foundation. I'm living in China. Today I want to introduce a use case. A China company migrate one of their application from Oracle to MariaDB. We just done the modified MariaDB version for this user last week. The application is testing in this modified MariaDB version without any application modification. This is my agenda. First, I want to introduce the background. Why the user wants to move to MariaDB, and then I will introduce how we got it step by step. The first is about the user requirements. This user case is driven by Hangzhou WatchTech, which is the MariaDB partner in China. The customer has some legacy applications using Oracle. The business logic is not complicated, and the workload is quite stable now because so many years. But they still need to pay an expensive Oracle license fee for these applications. So the customer decided migrating to open source database. MySQL ecosystem is the best choice, but the application is developed by ISV and is too old. The source code has been lost, so modify SQL is impossible. The only things we can do is to replace the JDBC driver from Oracle to MySQL or MariaDB. We need the database to be able to run Oracle queries directly. Why this user choose MariaDB finally? First, the customer decided to choose the MariaDB MySQL ecosystem because they consider this is the best open source database ecosystem. Lots of third-party tools, lots of technical documents. Many engineers are familiar with MySQL and commercial support. Then the question is MySQL or MariaDB. Why customer and WatchTech consider MariaDB is a better choice? Let's have a look about Oracle compatibility between MySQL and MariaDB. MySQL doesn't support most of the Oracle syntax and most of the Oracle data types. Migrating from Oracle to MySQL requires lots of changes to MySQL. We consider which is a huge project for years. And MariaDB already supports many Oracle syntax and data types, includes some PLSQL with Oracle SQL mode. And MariaDB already has an Oracle syntax tree. It's easier to add a new Oracle syntax support. So based on MariaDB is the best choice. Then how migrate from Oracle to MariaDB? The first, we should check the connection way because not all connection methods may modify to connect to MariaDB. The second, collect the queries of applications. The third, analyze the compatibility with MariaDB. The fourth, evaluate workload for modifying MariaDB code or application code. Sometimes, if you are lucky, the application can modify the queries or change the application code. Then you needn't to modify database source code. The fifth, adding Oracle compatible code in MariaDB. In this case, we are unlucky that the application can't change anything. The sixth, testing the modified MariaDB version in application to verify everything is compatible now. Okay, let's see these steps one by one. The first, check the connection way. If the application is connecting Oracle by JDBC or ODBC, then it's doable. We need only replace the JDBC driver to MariaDB. But if the application is using native C OCI lab, then we have no way to replace it now. The good news is WatchTech can support Oracle OCI Podcom in Reno proxy product at the end of this year. Okay. The next, collect the queries. It has many ways to do this work, like enable Oracle SQL trace, use $v$ views, like this view $v$ circle array. If you have a proxy, you can collect all queries in proxy layer. If you are lucky, the application is using the SQL framework like Abatis, then you can get all queries from it. The next, analyze compatibility. Sequence is a good project. Is a good open source project. It can help us to analyze if the queries can rewrite to another database or not. WatchTech has its own set of tools to analyze whether the queries collected from Oracle can be supported in MySQL or MariaDB. Alibaba Cloud also has a tools named Adam can do this analysis too. And then we need to evaluate workload. MariaDB has done a lot of Oracle compatibility work, like virtual2 and number data type, sequence filter, and many syntax compatibilities like from DUL, Oracle style, query procedure, and function. Except the MariaDB already done. For this case, we still have some compatibility work needs to do. For DDL, the Oracle has enable keyword, which is default behavior in MariaDB and can't change. So we can ignore this keyword in query table and index. For DML, the sysdate function in Oracle needn't brackets, but MariaDB requires it. We can modify syntax tree to remove it. About 3 tasks are very easy. Modify syntax tree can solve it. And Oracle has the toChar function, can convert the other data type to a string. In MariaDB, most of the time we needn't to convert them manually. MariaDB can automatically complete this work, such as between numbers and string. But for but for data time, we need to use data format to format it. This task is a little more difficult, but we can reuse the MariaDB internal functions. But we still need some changes. The most difficult work is row number. MariaDB can't support it at all, and we can't find the similar function. Sometimes it looks like a limit, but more complex usage. According analysis and evolution, we know which parts we must modify the code. Then let's do it. For task 1 and 2 and 3, it's easy. Modify circle yak file can done these works. It's quite easy. Just add keywords so that the syntax tree can recognize them. We can see. Okay, we can add the enable keyword after the fulfill the definition, and also we can remove the break side for C state here. So we can see after adding the keywords and alias, MariaDB can run Oracle SQL now. For task 4, we can reuse the data format function to solve it. SQLines provided a table of mapping the format specifiers from Oracle to Oracle toolchart function to data format function. Modify the make data time in item function file to support the Oracle format specifiers. In the same time, add toolchart function keyword in circle yak file here. Then we can see MariaDB can support Oracle toolchart function now. The most difficult is task number 5, row number. How we implement the row number feature. Adding row number. Our idea is adding row number as a virtual column based on MariaDB virtual column, and then adding a counter named current row number with default value is 1. When a row is read, set the row number field value to current row number. When row sent to client, then current row number plus 1. So if the query hasn't the while case, the current row number is the read sequence number. If the query has the while case without the row number, the row number field will return the sequence number after order by or aggregation. If the query has while case with row number, if the condition is row number greater than 1, it will not return any data. This is the same in Oracle. Once the result set from subquery contains the row number field, we will not add a row number virtual column again, which is the same with Oracle 2. After we have done these changes, we have solved all known incompatibilities. Then we can test the modified MariaDB in users' application. The first, we export and import the table structs and data from users' Oracle database to our modified MariaDB. Then start a test application to connect our MariaDB. And then to verify the application is running well, copy online workload to MariaDB through network traffic copy, and verify the MariaDB can support the online workload. Okay. Finally, let's see the progress of this project. This project kicked off on July 7, and we got the POC version on September 11. Although this application is not complicated, but the progress is based on MariaDB is so fast and beyond our imagination. Okay, this is all my presentation. Thank you.
Now for a hardware-related presentation by Krunal Bauskar, MariaDB on ARM.
Hello, welcome all. My name is Krunal Bauskar and I have been driving this MySQL on ARM initiative. As part of this initiative, today we are going to talk about MariaDB on ARM. I'm sure you would find a lot more interesting thing about MariaDB on ARM, and it will help you make a choice whether you should run MariaDB on ARM. So let's get started now. That's quick intro about me. I have been working in MySQL space for quite some time now. I have also worked with Percona as a PXE product lead, managing all aspects of the PXE, including performance. Before that, I worked with MySQL Oracle team as InnoDB developer and worked on some of the features during 5.7 timeframe. Also in past, I've worked on big data problems at Yahoo Labs, or I've also worked on a project for a startup, which is now part of Teradata. And we made the world fastest storage engine for MySQL and lot more such projects. Currently, I'm working at Huawei as part of open source DB group and responsible for all flavors of MySQL ecosystem, which include MySQL, MariaDB, and Percona. So as I said, I've been driving the MySQL on ARM initiative. So with that quick intro, let's now get started with our talk. So that's our agenda for today. So first we will see ARM ecosystem. We will try to understand why ARM ecosystem is gaining traction and why it is important. Then we will talk about MariaDB and ARM. And then we will see how MariaDB performs on ARM with some performance number. Towards end, we will talk about the state of ecosystem. So with that agenda set, let's get started. So first thing is ARM ecosystem. So I'm sure you have heard of ARM processors, but the context in which you have heard, probably most of us have heard, is mobile or network equipment. Most of our mobiles are powered by ARM processors because ARM processors consume less power, and so they can use the battery better. Now, if you stretch your thinking further, you would observe that ARM processors are also widely used in housing appliances. A lot of housing appliances use ARM processors. If you stretch it further, you would discover that ARM processors are also used in automobiles, especially self-driving cars, and with increasing automobile using electronic circuitries, defense space where the usage or usage of power is important. All these kind of application ARM processors have been gaining traction. Something which is new is HPC. HPC stands for high performance computing. Most of our products like application server, databases, big data falls under HPC. So thanks to the performance per watt, as I said, ARM processors are better at are optimal at consuming power, thereby reducing the cost of ownership. And they are getting more and more powerful with additional computing power that makes them a suitable choice for even use in HPC. Now, something which has changed in past couple of years is few years back, if you wanted to boot a very strong ARM instance for running your HPC application, there was nothing available. But in past couple of years, a lot of cloud providers have started offering ARM instances. For example, Huawei Cloud offer a ARM instance using its high silicon Kunpeng 920 processor. AWS offer ARM instance using Amazon Graviton 2. There's another startup called Ampere, which is trying to develop ARM-based cloud-ready ARM-based processors under Ultra series. So with options available, developer can now easily port their application to ARM, and user can eventually start directly running their application on cloud using ARM instance. But only having hardware doesn't help. So the software also has to be evolved, and that's exactly what we call as ecosystem. Fortunately, in past few years, all major OS providers has been able to provide OS support or OS releases for ARM. Then beyond that, if you look at projects, right, the applications, so most of the applications now are either supported on ARM or work in progress. For example, big data, the Hadoop, which was the base for big data application, is already now supported officially on ARM. Application servers, load balancers, databases are most of them are either work in progress or supported on ARM. Now, ARM Cloud Instance, so the reason why ARM is gaining so much of traction is in ARM is supposed to generate a direct saving of 30% by keeping performance on par. So that has been the motivation or USP why ARM is gaining so much popularity. So strong presence of ARM on data generating device is also going to fuel why ARM should be also used for backend server. So your complete end-to-end ecosystem chain is could be booted on ARM. Now it is estimated that by 2030, most of the HPC application will be running on ARM instances. Let's see, it could be earlier based on how the things evolve. Okay, so with that, a short intro about ARM ecosystem. Now let's talk about MariaDB and ARM. So fortunately, MariaDB is already part of ARM. MariaDB has been releasing packages for ARM on distros like CentOS and Ubuntu, while there is a work in progress going on to add support for more distros in near future. So we are hoping that almost all the distros, major distros, will be supported. MariaDB not only support MariaDB server on ARM, they have spent good amount of time and efforts to optimize it on ARM. We'll see what some of these optimizations, but as I say, optimization is a never-ending process, so the effort will still continue. In fact, MariaDB was first to add support for ARM. And as I say, MariaDB has a full support or GA, which means all your bugs, whether it's functional bugs, correctness bug or performance bug, will get addressed with the same priority like x86. So that makes MariaDB an ideal choice as a database or open source database to be run on ARM. Now, when you add any additional architecture, you need to face some basic challenges, and ARM is no exceptions. So let's understand what challenges are involved when you port any HPC application to ARM. So ARM is a weak memory order. We all know it's a weak memory order. So to get optimal performance, proper memory ordering has to be used. x86 is a strong memory ordering. So if you are just reporting the code will of course work, but will not get optimal performance. Thankfully, C++11 added a support in its standard for memory ordering, and MariaDB being C++11 compliant was able to harvest this memory ordering support and make optimal use of memory order to get maximum performance on ARM2. Tuning code for ARM. Now ARM is a different architecture altogether. So low level loops or basically code like spin loop, right, needs to be readjusted. I would say readjusted and retuned for ARM processors, because the instructions for pause are different. How much time you want to spin would be different based on the frequencies and all. So accordingly, you have to make sure that code is retuned for ARM processors. So ARM is all about more cores, maybe less powerful, and more. That means more NUMA nodes. So any software that needs to have given with more cores should able to use them efficiently. What I call it to be a NUMA compliant or basically a NUMA optimized software. MariaDB was already NUMA compliant or optimized, since x86 also has multiple NUMA nodes. But additional cores, how to make use of additional core, MariaDB actually have tuned or have solved a lot of scalability issues while working on ARM. And I could say that MariaDB is now completely pretty well optimized for more cores that ARM processor throws at it to make maximum or optimal use of these processors. Beyond that, ARM do provide some acceleration instructions in form of Neon SIMD LSE So atomic instructions, special atomic instructions, or optimizations of it. So all these, even with vectorizations and all these things are also provided by x86. But since the code, or these are low-level hardware instructions, you may have to write a parallel code along x86 for ARM purpose too. So making sure that you tune all such code snippets and enable them for ARM from optimization perspective is also important. ARM has a different cache line requirement, so making sure the cache lines is adjusted. Alignments, memory alignment hints could be needed. There could be pipeline differences. A code which could be hotspot, which is not hotspot on x86 could be turned out to be on hotspot on ARM. So making sure you discover such code, retune them is needed. And switching to use hardware optimized support. So there are few functions which hardware can also do. For example, very good example of this is checksum. So when x86 also provided such functionality where it could compute some of the things directly at hardware level, and they're faster. And the same support is also offered by ARM. So making sure that you discover such code and get it ported and use the relevant functions from ARM hardware architecture is important for making software performance optimal. So these are few challenges that any HPC software will have to face, and of course MariaDB has already faced. So if we look at the complete solution, all the issues, then you could this is a partial picture that we are trying to provide. MariaDB have addressed almost on all front some optimization has been done, whether it's memory ordering. So memory ordering has been taken care of. We just talked about one of such challenge. NUMA scalability, even on NUMA scalability like spin lock optimization, timer counter optimization, cache line sharing, all such more optimizations has been taken care of. Whether it's use of neon, even that has been taken care of. Moving to atomics so that it is able to scale correctly. Use of checksum, we just talked about the checksum example, making sure the hardware checksums are used. So when MariaDB made optimized MariaDB server for ARM, they made sure that the optimization is not only done in one direction, but all aspect of optimization for HPC softwares are taken care of. And the result of this is the complete upliftment on all scenarios, or I would say all use cases. You could see that MariaDB server on ARM performs better. So all these good optimizations, let's understand how they are going to help. Okay, so only one way to find out is by benchmarking. So we will try to look at some of the benchmarking numbers with this. Before we get into the real benchmarking, let me introduce you the cost performance model. I'm sure you might have heard something similar to this in past, but let's talk about it, what I meant by a cost performance model. If you boot a ARM instance and if you boot an x86 instance, roughly with the same size of computing power and memory, you would see that almost on all cloud provider, ARM instance provide a decent saving, anywhere ranging from 20 to 50%. So that is expected because that's the USP of ARM resources. So of course, the idea now would be that can we leverage this cost saving and still get improved performance? So if I can run the same software on x86 with the same configurations and on ARM, and if I could still get on par performance, I could say that I have achieved a 40% saving. Okay, so this is the existing model, but there are challenges, right? The challenges are CPU frequencies when you compare two instances of ARM. Like here, if you compare on Huawei Cloud, the Kunpeng ARM instance is 2.6 gigahertz, while the respective instance of x86 is have a base frequency of 3.0 gigahertz with a turbo frequency of 3.4 gigahertz. So these frequency differences make the comparison challenging or basically not on par. Beyond that, Intel has turbo mode, which means on lower scalability, Intel is always going to score because it is going to use its turbo mode. Now CPU generation differences are also there. Now Intel itself being in race for quite some time now, it has its Broadwell, it has Skylake, it has Cascade Lake, and more such things. So there are CPU generations differences. Now x86 cores have physical core. There's a concept of physical core versus HT core, what we call as hyper-threaded core, and what cloud provider provide you is vCPU, right? So there are these differences. There could be NUMA arrangement differences. NUMA make a difference, and with increasing cores, more NUMA nodes will be there. There could be memory differences. Scheduler, what I've heard is with Linux kernel 5.x, there is improved support for multi-NUMA architecture. So that's another thing to consider. So with all these things in place, it's important that we can't directly compare, or it would not be an apple-to-apple comparison just for purpose of cost saving. So we developed a different model, or we just proposed a different way of looking at it. What if we could say we could keep the cost constant, and let's analyze if we can get more throughput on ARM, thereby turning into more TPS per USD. So if I put it more formally, if I have X USD to be spent, what I'm going to do is I could get M ARM resources and N x86 resources, of course more ARM resources. Can we get increased performance from these M ARM resource? So for cost constant with ARM resource, I'm getting more performance, thereby it is increasing my TPS per USD. I put it more into form of definition. Given the on-par cost of both the resources, can we exploit ARM variant to its fullest benefit and get better performance when compared to x86? I think that's fair enough to consider. So let's understand whether we can apply this model and then analyze how ARM performs with respect to x86 using MariaDB as an example. So this is just a quick example of if you try to boot a VM on Huawei Cloud, almost of the same cost, x86 and ARM, you would discover that, and the memory is also same. For the keeping all other configurations same, it typically looks to be that the computing power is almost double. Okay, so there are 2x more core. I shouldn't say computing power because there is a frequency differences, but let's assume that you can get almost double the cores or 2x more core for ARM. Now these extra computing power is surely going to help you scale better on ARM versus x86. The difference looks to be 2x on VM. With bare metal, this difference further increases. So we'll see, with how this particular extra computing power is going to help us. So this is a typical setup that we will be using. So this is all testing is using Sysbench. So most of us would be familiar with this. We would be using data which is of 69 GB in size. We will be testing it on two things. One is a CPU bound workload where we will provide enough buffer pool, and an IO bound workload where we will provide lesser buffer pool. Redo log is good enough too. We would be using two different versions of MariaDB, 10.4.13 and 10.5.5. So 10.5.5 has some performance regression on the flushing front. So which is actively being fixed by MariaDB team. So just for a fair comparison, we will use one older version where this particular regression is not present. So we'll get a good idea of how ARM is performing. And we'll also see the result in 10.5.5 where also ARM is performing. So test scenarios, we will look into Sysbench, point select, read only, read write, update index, update non-index. Machine configuration, we have used a bare metal and we have applied the CPM model. So for the same cost, we could get 28 HT core of x86 and 64 cores of ARM. Okay, so that's the normalization done on using CPM. And storage, we have kept the same storage for both of it. The IOPS are almost or comparable on both of the storage. So that's the short, that basically by keeping all the other configurations same, only by changing the computing power, that would make it easy to evaluate whether ARM really perform. Okay, so with that, Let's see the results. This is MariaDB 10.4.13 workload, CPU bound workload. The the blue line represents ARM and red line represents x86. As you could see, almost on all use cases, ARM continue to perform better than x86. Importantly, with increasing scalability, the difference of performance further continue to grow and ARM continue to surpass after some point. In fact, for read-write workload, the difference continue to be better with significant margin with the ARM. And even for read-only workload, bearing some small crisscross, we could see that ARM has been able to perform quite better on all the use cases. Now that's CPU bound. Let's talk about what about IO bound. So IO bound also present the same picture. As you could see, for all IO bound workloads, ARM, which is again a blue line here, continue to scale better and surpass or beat x86 on almost all front, including read-only and read-write. So this is MariaDB 10.5.5. As I said, MariaDB 10.5.5 has some performance regressions, which are being actively fixed. But I thought it is worth adding the results. And as you could see, even with this, ARM continue to beat x86 with increased scalability. So again, one thing which is prevalent is that on all these workloads, ARM scales better. Thanks to the extra computing power that is present for the same cost, that is making it scale so better versus x86. TPCC. So this is also gaining quite a lot of traction, or people do use TPCC also for a lot of validation. So I thought I will also add this results just to check how it does. And as expected, ARM continue to perform better than x86 quite significantly with increased scalability. Even for lower scalability, difference is marginal. I would not say it's a huge difference. So difference is marginal. And once the scalability point cross, then ARM just picks up and perform almost doubles the throughput compared to x86. Okay, so all these numbers, but then eventually probably we want to put them into some numbers using which we can justify the cost saving. So this is just an example. I have assumed the cost of the machine somewhere about 800 USD, and then I tried calculating TPS per USD. So I'm using one such data point, 1024 thread update index use case, and this is with 10.4.13. We use both CPU and IO bound. If you look at the numbers, then the TPS, that is transactions per second, for ARM is always higher than the transactions per second for x86. Now that effectively means the TPS per USD is of course better for ARM, and that directly translate into a saving, because for the same cost I could get more work done from ARM versus x86. Now typically, if you want to put it in another way, I would say there's a point when you would hit a threshold and you will have to take a decision that, well, I have to increase my computing power. So you have two options, right? So either you can go and buy a bigger x86 machine at extra cost, okay, and get your performance scaled, or you could simply keep the cost same and switch to use of ARM and still get a better performance or increased performance. So that way it directly translates into a cost saving, even in form of clusters. If you have a master slave configuration, then of course you would find out there too, if you are booting a 5-node cluster of x86, maybe you'll have to boot a 4 or 3-node clusters of ARM, and which effectively will generate a significant saving. So from all these experiments, it is very much clear that MariaDB on ARM is a cost-effective solution as compared to the other flavors. So with that, let's talk about the state of the ecosystem, because when user adopt a software, he needs to also make sure that the ecosystem is up and running. So that's a quick intro about ecosystem. as you could see, the green blocks are already present on ARM. So server, of course, is there. Backup is inherent tool of server, and so is the cluster solution, whether it's Galera cluster, multi-master solution, or Binlog. They are part of the MariaDB default server. Things which are in red are not yet part of the ecosystem or have official packages on ARM, but they do work. For example, a few days back, someone from Percona actually compiled PMM or Percona Monitoring and Management Tool on ARM and was able to compile and get it running successfully. Now, with community support, we can actually make sure that all other remaining components also are made available on ARM in form of official packages. So the question is why we aim for completion, because if you are running part on, of course, you can still run part of these components on x86, because anyway, they will talk MySQL protocol and they can communicate with the server on ARM using that protocol. But having everything on x86, on ARM would help you get significant cost saving. So I think that is the reason why we should aim for completion. There are other supporting tools of the ecosystem. Like for example, if you are running on Kubernetes, it is available on ARM. If you use VTest for sharding, then probably it should get available on ARM. So with community support, if we start asking, then respective organizations which own that tools or have been developing that tools could make them officially available on ARM. Same with migration tools. So that's why I think the community support is very important for upliftment of this ARM ecosystem. Whether, like we just talked about PMM, there's a Jira ticket open for max scale packages. So go ahead and like it. MariaDB will surely consider it if there are more community interest on making max scale packages available on ARM, connectors on ARM. As I already talked about distro, for distro we are already talking with MariaDB organization, and they are going to add more distros beyond CentOS and Ubuntu. So I think this is going to, community support will always help. And as I say, development still continues, right? So MariaDB, ARM is on their mainline plan. So they do consider ARM compatibility while they develop any new feature. The DB community is growing. They have contributed a lot more performance patches, bugs, making sure that ARM64 wider hardware compatibility is possible, because ARM is an open architecture. Lot of companies develop their own ARM processors using the main design. So making sure that the software runs on all these ARM processors. And if you have any issues and if you wish to join or contribute back to MariaDB on ARM, there is a dedicated channel on community chat of MariaDB now, which is called MariaDB on ARM. So I'm going to end this talk leaving you with a message which says, let's make MariaDB great again on ARM this time. We all know MariaDB is great on x86. We are just saying that let's make it great again on ARM this time. Hope you all the community people would be able to support this. And next time when we talk about it, MariaDB on ARM would be the best open source DB available. Thanks for attending. If you have any questions, you can of course put it over Twitter. I have also an active blog. There's also GitHub. You can find my contact details also. So if you have any questions, of course you can ask on the channel also and post it to me too. Thank you for your time and thanks for attending the talk. Thank you.
The next presenter is from MariaDB Corporation, Richard Bensley. SQL mode equals ludicrous.
Hello everybody, my name is Richard Bensley and I work for MariaDB. I'm actually a software developer. I'm working on the monitoring team for SkySQL, our new cloud platform. But I've been invited to talk about my little talk that I've entitled SQL mode equals ludicrous. I've got about half an hour with you all just to cover a couple of scenarios of how I've used MariaDB in production environments in probably the most nonsensical ways possible, or at least how I've used some of the more interesting underlying features that I've previously found as a DBA to really help me out in production environments, not just in production has failed or something has gone wrong, but also how I've kind of used a few little things in system design, which I've had to like design, create, maintain, which has actually helped our environment. So I hope you enjoy it, and we're going to have some fun now. I'm going to kick off with my first example using my favorite tool. The connect engine on MariaDB. I was a very early adopter of MariaDB 10 when it came out, and the connect engine was one of my absolute favorites. I was working in a mixed database environment, so I jumped onto the ODBC connector very quickly to start querying other databases, not just MariaDB, from afar. I started using SQL from a database to query other databases, and I'd use it for reporting, materialize use, data warehousing, ETL, ELT, all sorts. The Connect engine documentation is vast, and it supports more than one table type, not just MariaDB, not just ODBC, but all kinds of table types you can start using. And one stood out to me in particular, which is the ini table type, which also happens to be very similar to the server config file format. I thought this could be quite interesting. How can I use this? The ini table type itself is what's called an outward table. So that means when you create the table definition inside MariaDB using the Connect engine, you have to define the table name. And I did actually have a use case for this. If I just get back to my terminal, there we go. I've just got Linux, MariaDB 5, 10.5. Not 5, that'd be very, very old. 10.5 running on Linux. I've just got a little custom environment here set up in a way that kind of resembles some of the production environments that I encountered before, and it'll kind of take me through these scenarios. So I had this scenario where MariaDB was new to us, MariaDB 10 was new to us, and so was Linux. We're still mostly on Unix at the time. Still, after 2010, there's still plenty of Unix shops out there. And whilst the sysadmins and DevOps trying to figure out what the DBAs should do now, and where the database should live, they just gave us a directory and said, you own this, you run everything as this user, and you've got some network mounts. I said, that's fine, we can just customize everything like that. In this case, we had a /mountdb kind of looking thing, and I just kept everything in one place. I could demonstrate that inside the server config, quite simple. Just foreseeing the socket connection for some clients in case they need it, because the default Unix socket authentication is fantastic, but I do just have to tell it it's not a default location, as I have customized it to be inside this directory. My Linux user is Vagrant, as I'm using Vagrant in VirtualBox to run this environment. So I'm running the database as this user on this system, not using the typical MySQL Servers account. So in theory, the DBA owns this environment, the files, the data directory, everything involved. And I've got just about everything I need here for the examples I'm going to be talking about today, including the Connect engine. So in that scenario as well, like you can see I've got plugin load HA Connect, so it will load on startup. And if I just go to the server now, show engines, I've got the Connect engine listed there. There we go, that's fantastic. So I had an environment where I could edit a lot of the server configs. Well, we could edit a lot within directories, but we actually packaged this stuff and we had to move it away. So we didn't always have SSH access to a box. We just package the database up with everything we need in it, SQL, baseline schemas. We could get it up and online from far away. Then we could connect in, perhaps set replication properties if we needed any, and whatever else we needed to customize. So we didn't always have file system access. This is very important. We own these data directories, we own these databases, but we didn't always have file system access. Here, enter the Connect engine any table type. So we normally have, I think most people have probably seen this in their environments. They've got a schema or a database called DBA. In there is all your DBA tricks. And I've just got one table in here today called CNF. I'm also going to show you how I made that with a show create table, CNF, XG. Here we go. So I've got quite a simple table definition, and this actually matches the config file format that I showed you previously. That the database that MariaDB is running, and it owns that file. It's got permissions for that file, so it's using the same user. And it's an outward table, so I've got a file name defined. The engine is connect, and of course my table type is ini. So let's have a look at what this table actually looks like. Let's select star from CNF. It's not a huge table. There we go. There's that ini file. There's that server config as a table. Let's update it. Actually, I've got a copy paster over here. I'll just grab this, run that. Oh, and it included the end of line as well. So it ran it for me. That's great. Just to go over what I did, I updated the table and I set the variable value for the log output. For those that do or don't know, the log output changes where the slow query log and the general log goes. So it defaults to file, and I did say file inside the config. But you can also set the variable value to be table, and they appear inside the system schema. So I was very specific. So with variable value, with the variable name equals log output, and the section equals MySQL D. So it's quite handy that you can see my client section is up there. I said I had to specify the socket for my clients. And previously the log output was set to file, and I just updated it to table. Let's select star from CNF. Let's have a quick look. Ooh, it worked. I just updated the server config from the SQL prompt, potentially remotely. This is extremely dangerous, but it's a lot of fun and could be quite useful in some scenarios. And I definitely found it useful where they kind of set a database up for me. They want me to connect in and test things, but things aren't quite right. If I wanted to get something changed, it might take an hour, it might take a day, I might have to wait to a change management window before I can actually make that change. Some things like this are a little innocuous. Of course, if you have a change management process, I'd stick to the change management process. But it was a nice little addition, and for various other table types like JSON or CSV, it was nice to have another method to connect in, edit and read files, particularly as DBA, particularly in restricted environments. So that was quite fun. I'm just going to set that back. I'm just going to update that back to a file. I don't want any surprises at the moment. I'm just going to shut down the instance as well and maybe restart that. Make sure it comes back. Do not want a dying instance during a presentation. That would be terrible. Show schemas. Are we there? Show process list. We're up and running. Select log output back to file. That's fine. Okay, so that was quite fun. And that in the same place, again, working with restricted access and having to go through jump hosts and things to gain access to production instances, we had a production instance which failed. And I like to call this little scenario the backup battle royale. So we had a failing instance, and everyone was looking at it. I myself had a remote SQL shell logged in, similar to the very dangerous Connect engine session I had open there. So I could actually poke around the database to see what was going on. There was minimal database activity, which was good, but the rest of the system was having lots of problems. and this system was going down. The sysadmins told us this system is going to go down, and if it doesn't, we're going to take it down. You need to put your stuff elsewhere. So, well, okay, we could do that, but the backups were from this morning, and they were already too old. The rest of the business was adamant we needed up-to-date data. So, okay, we can't get the bin logs. When they tear that system down, the binary logs are going to go for whatever reason. I was the last user left alive. I had my SQL session, but we also had one extra thing, which was the backup. Where we put the backups was a network mount, and the database could write to it. And I whipped out my favourite tool, Outfiles. I'm sure people have used Outfiles on and off over the years. It's by far one of my favourites. It's so simple. Along the vein of Connect Engine, I can just interact with the disk as well as remote things. And I can put files, I can just select data and put on a disk. The default format is tab separated, so I'm going to use the TSV as my extension when I start working with things in a moment. And I've always found this super useful, not just in some odd backup restore scenarios like this, but also just in, lots of people have probably used it for ETL, ELT, for loading in and out of column store in particular, or another system, or just doing an archive backup, export into CSV, TSV, upload to a bucket like S3. However, in this scenario, I was trying to get up-to-date data from a failing system. I've got a database in here called Jam, which is a fictional jam factory where you can order jam from. And I've got some tables. Let's have a look at some tables. There we go. Let's start from T_jam orders. Oh, well, it's 10,000 rows. I was going to do a count. There we go. Count 10,000. Don't want to see every single row. That'd be terrible. Good thing there wasn't a billion rows. Good thing this wasn't column store. That'd have been many more rows. I'm just going to create, for this example, I'm just going to create and load a table locally from disk using the in-file, out-file interface. So I'm going to select everything from the jam orders table and put it into another table. So in my actual scenario, these are remote databases. So what I'd export from one database and put it somewhere else. So we can get your database up and running somewhere else. Give me 20, 30 minutes and I'll get it done. It wasn't a huge database, but it's still important data. So I'm just going to create a new table like that table, and I'm going to call this new table New Table. Next, I'm going to select star from jam.t_jam orders into outfile. This is where the magic happens, and I'm going to specify a path of where I'm just going to write to temp. Everyone can write to temp. That's very handy. I'll call it jam orders dump.tsv. There we go. And I've exported 10,000 rows. Let's have a quick look at that on disk. WC-L temp jam orders dump.tsv, 10,000 rows. So if I just tail the last 10 lines, you'll see that this is just a, so this is a row per line inside the file. And you see it's tab separated. That's the default format. You can specify more options, as you can see in the documentation. Well worth reading. You can specify the delimiters and what it's terminated by. Particularly handy if you've got perhaps some funky characters going on inside your database tables. But we don't for this scenario. Pretty simple. Date times, integers. Nice and easy. I'm just going to go back to the jam database. I'm just going to select count star from new table. Nothing in there. That's fine. Now I'm going to load that table using the exported data. Load data in file, and it was /temp/jam orders dump.tsv into table jam.new table. Genius new. Load data in file into table. There we go. I'm just going to select from that table again. Select count star from new table. There we go. Show create. New table. there we go, just the regular InnoDB table, and we've exported the data to disk and loaded it from disk. So my scenario, that was a network mount, and that was a lifesaver. We kept all the schemas inside version control, and I always thought if that wasn't there, my last-ditch effort would have been to clear my terminal, did a show create for everything, every store procedure function, every table, and put that somewhere else, then just do the load data. Thankfully, we did have the schemas and all the database objects inside version control, so I could quickly get that up to date, restore the backup, then just load the difference. For a couple of tables, I just dumped and loaded everything. For some, I loaded the difference, and that was a lifesaver. That made a big difference. I'm just going to drop that table now. Drop table, new table. I'll get back to where I need to be for the next little issue. Oh, just one caveat for in-file out-file. The only caveat which you might encounter when using this is so that file already exists, the out file I created. So if I select star from jam orders into that same file, the file already exists. That's the only caveat with the in-file out-file interface. If you're creating files, you do need to make sure that what you created doesn't exist before you do it again. So it's a shame you can't overwrite it. I guess it's kind of a security feature. And in better practices, I'd script this and I'd append a timestamp or something to the end of the file name. So it's a little bit more descriptive other than just this. But for an example, it's fine. Now I can run it and it's fine. Okay, let's go remove that file again. All right, let's clear screen and go on to the next example. Casual conversation one morning with a colleague. Somewhere, someplace, sometime. They were developing a new system, and MariaDB was now the new tool of choice for everyone, which is good. We did our jobs as DBAs. We canvassed development globally, and we got them convinced, and they were all very happy, and they'd already seen some of these kind of other things we were doing, so everything was working very well. Until the conversation came up, we've got something new. But if it gets big, how do we scale it? I said, well, don't worry about it for now. I said, let's just get binary logging enabled, and then when you're ready, we'll come do a bit more consultancy with you, and just set the bin log format to row. That's all we're kind of looking for, and just make sure the expiry is longer than the restore time. We said, well, what does that mean? So you've got an option to set the binary log expiry. So if it takes a day to restore your database, you need at least 2 days worth of binary logs. So if that restore doesn't happen, you're going to need to, if you've got another server downstream or upstream that's serving requests, and they're kind of running out of time, you need to make sure your backups and your binary logs are all in sync together. So you backup and restore to a certain point, then you might use your binary logs to do a point-in-time recovery, to restore up until it's absolutely necessary. For some people, just a daily backup and restore is fine. But for a lot of customers, the scenario is a bit like that in-file, out-file scenario. Bin logs weren't available. We couldn't use a backup. It was too old. Or the backup was up to a point. So I essentially did a point-and-store recovery with TSV files, just plain text files. And it did kind of work. In a normal scenario, you'd use binary logs. It's a much more robust scenario, robust solution. As I say, take a lot of this with a grain of salt, but I had a lot of fun in production with MariaDB. And we solved a lot of neat problems. So anyway, I don't hear from this team for a little while, and suddenly they call up and say that the customer's using this instance. Okay, how can we help? Well, we need to dump and restore it to another database, but we don't have any backups or anything. And in fact, we kind of lost access to this instance. It broke, and they need to restore it. That's essentially it broke, and we need help. But they didn't have any backups. However, they didn't actually set a binary log expiration. I said, because they didn't have any backups, they didn't have something to set it to. They said, well, we'll just keep it forever. I said, that's even better. That's fantastic. Don't worry about the backups. We'll get you up and running on a new box, and we'll apply our DBA standard to it. So there's monitoring and backups and point-in-time recovery and alerts. And we'll just restore the entire database using the binary logs. They thought that was magic. I'm going to quickly whip through this example. I'm going to use my jam database. again. I'm just going to show you there's nothing up my sleeve. I've got some different queries just to make sure I've got what I need. So if I select count a sum from the orders table, there we go, a sum of just about 1 million orders. And now I'm going to just delete everything from these tables. Just do a quick sum again. Okay, I'm just going to look at my existing binary logs. Now I'm just going to wipe out these binary logs. I'm just going to reload this database for an example. So if I do a quick select star again, so these tables are now empty, and it's a fresh database, if you like. I've got no more binary logs. If I show binary logs again, we're back to nothing. Okay, so I'm going to emulate the scenario that we are in just by using a little Python script I put together to populate the Jam database. So I'm just going to load that with data. So in theory, they started a new instance, they started loading data, they were creating tables, creating schemas and objects and all these kind of things. And while they didn't have a backup, they did have the entire binary log history. So in my case, this is only going to be inside one file. We started at 325 bytes on binlog 00001. If we just go have a quick look at the database and show binary logs, we'll see that the position counter has now moved on because we have loaded data. Now, just to have some fun, I'm going to, again, I'm just going to flush logs to move me along one log. So now we should have 2 binary logs. There we go. So now everything I do new will be recorded inside this next log. Easy peasy. And in this new log, I'm going to delete everything again. Oops, let's use Jam. And let's just delete everything again. So if I run my quantifier, there we go, aggregate function. We're back to 0. We're back to no rows. But that's okay, because I know there's one binary log there with all the data inside it. So I'm just going to go to db/data, and I am going to use the binary log command to replay the binary log against the instance. I'm just going to copy paste. I'll talk through it rather than copy pasting it. Of course, everyone noticed the new binary names are available. So instead of using MySQL binlog, I'm using MariaDB binlog. The binlog I want is 001. It's the first one. I'm only going to replay one set of database events from the Jam database into the instance, into the database, Jam. I'm just going to let that process. Perhaps I can see what's going on inside my show process list. There we go. So that's going to go through. But, oh, we're done. It was too quick. Too quick. Okay. -A, Jam. Let's go back to the database. So we had no orders before. Let's do a quick quantity on there. There we go. Fantastic. Who doesn't love binary logs? Managed to restore, dump and restore the entire database using binary logs. Very handy. Right. Hope you enjoyed that one. I'm going to cover one more scenario before I leave you all. I think most developers, DBAs, have come across this scenario before where the first thing, I've heard the story so many times, you join as a new DBA, you don't know the circumstances of you joining or the previous team or people leaving, but you've got like a database, or perhaps you've just been hired for a particular set of databases they've got problems with, and the first thing you do is lock out every single developer. Well, I did need to do this, but I didn't need to be so. I didn't need such a sort of blanket ban of all developers. What I had to actually do was lock them out of different regions, and for reasons I can't disclose, the servers in each region would be rolled over. So the master or the primary would change to each region as the world turned and the sun rose for another day and somewhere else. The new primary would move. But it also meant if developers were doing overtime in their region beyond 5-6 p.m., they could stay inside their own region, but they could not log into the new region. And we did that on purpose so they wouldn't fiddle with the current primary. So to fix this, I came up with a solution which I found in the documentation years ago. I'd seen this around init connect and init file. Init file is a server variable you can put in there, pointed towards a file full of statements, and that's SQL that can run during the server startup. Init connect covers SQL, which is executed when any user connects. This is terrifying, and I use this in production to control user access, and I'll show you what I mean. Some of you may have seen inside my config file before, db-my.cnf. I've got a little line up here, init connect call auth check user account. So the connect SQL for me is a store procedure which is run. Let's go and have a look at that. So I've got a database called auth, and this is where I stored everything related to this region lockout mechanism. If I just do show create procedure, check user, I think I should call check user access. There we go. I just three variables, just who's the current user connecting, an integer just for allowed, 1 or 0, 1 is allowed, 0 is not, the process ID, which is the user's current process ID. And you'll see in these, I just set the current user to be the current user from the user function, and I select allowed from a table where username equals current user into the allowed variable, and then I just grab the connection ID into vProcess ID, and if allowed is 0, then this select statement shouldn't actually render anywhere at all, but kill process ID. Just there for just to be a bit more clear, and I just kill the user's process ID if allowed equals 0. So let's select star from users. So everything except my jam user, root user, test user, vagrant. I've got one user here, test user, who's a bit of a troublemaker. Is not allowed to log into this particular region. I used a non-replicated table to maintain these tables in each region, and it worked well. So if I try and log in as this user to this database, it's going to read from this table using the store procedure, and it won't let me in. MariaDB -u is test user. The password is trouble. Okay, I'm in. May look like I'm in, but I'm not in. Do a quick show schemas, for example. Connection aborted. That's it. Init connect command failed. We're done. We're done. No access. Okay. Well, let's flip that on its head. Let's set allowed for the auth user. There we go. Select star from users again. There we go. So all users are now allowed. And let's try connecting again with our test user. We'll do a show schemas. Now we're in. Now we can use MySQL and select star from user, because we are a troublemaker. So that was a very simple mechanism. Do I recommend it? No. It takes a lot to maintain that kind of scenario, but if you're comfortable with this kind of like change management and testing, always test, then you'll probably find it a very useful feature. And you could do all kinds of things. The init file I've used quite a lot in container scenarios. So a new server comes up in a container and I just want it to run some extra SQL. Perhaps have a container that's kind of more ready to go, rather than having to load a container as an afterthought. I can have a Docker file or something which actually loads a database on startup. It's probably one of the most dangerous but more interesting variables I've come across, or features I've come across. I hope you have some fun. I hope you kind of come away from this thinking, I'm not doing any of this in production ever. That's good. If you come away from this thinking, I'm going to do some of this in production, that's also good. I highly recommend experimenting with the Connect engine, what you can and can't get in and out. The in-file, out-file interface has been an absolute lifesaver for me. Just get data out, put it somewhere else, bring new data in, script it, automate it. Just remember, you can't overwrite the files. The init file has been a lot of fun for me, and of course, become familiar with replaying bin logs. You can do a lot of magical things, and in that particular scenario, I just restored one database from the binary logs all the way from scratch, and it worked great, and they were really happy. Thank you for listening to me, and I hope you enjoyed the rest of the Serverfest.
Our next presenter, Yang Chen, MariaDB at Bilibili.com.
Hi, my name is Yang Chen. I'm working as Senior Database Engineer at Bilibili, and today we're going to talk about MariaDB at Bilibili. A talk focuses on how we use MariaDB at Bilibili and MariaDB architecture at Bilibili, and how do we make database formation, scale up, and so on. And first of all, I would like to introduce what is Bilibili and what's major business. Our website is www.bilibili.com. And Bilibili is one of the most popular websites of China. It's an online entertainment community for young people, and it's a free video sharing website which makes it easy to watch some online videos. And instead of videos from major TV networks and movie studios on Bilibili, you will find something special, just like animation and comic, gaming, and study courses, and all kinds of amazing and creative videos made by some young people just like you. And you can even create and upload your own video to share with others as well. Moreover, we have live streamed e-commerce, gaming, and so on. And we have more than 170 million active users every month. Okay, here you can see, here is some screenshot for Bilibili website. You can try to go and find something interesting. It's more like a little YouTube of China. Okay, so here is why do we use MariaDB instead of MySQL. That is because MariaDB is made by the original developer of MySQL and guaranteed to stay open source. And MariaDB does not have closed source modules just like the ones in MySQL Enterprise Edition. So it's built upon performance, stability, and openness. And MariaDB Foundation ensures contributions will be accepted on technical merit, and also MariaDB supports some more important storage engines such as Aria, Spider, DB, and so on. Also, it has a lot of great features such as thread pair, faster and safer replication, instant auto tables, and so on. Okay, here is how do we use MariaDB. Where do we use MariaDB? We use MariaDB for user informations, member and relation data storage, and also for website, API, and authentication request, and almost all the metadata with videos, live stream, gaming, and so on. And also, for some store, and for some e-commerce orders and payment information in MariaDB. And basically, it's used almost all business units of business. And what's more, all sensitive data are encrypted to protect privacy, so it's very important for our users. Okay, so this is the situation for MariaDB at Bilibili. We have several data centers for business requirements and disaster recovery, and solid MariaDB servers, and there are managed by automation system. We use Ansible for server management. And also, we use GTID for MariaDB replication management. And all of the production MariaDB servers are 10.1 and 10.3. And we are running with max 45k QPS for single instance. So you can see maybe we're not very large, but very busy. Because we have live stream business. In case of some popular esports competitions, the online room concurrence will be several millions, so which makes a lot of service traffic at a very short time. To the next page, we are going to see what we DBA team are planning to do next step. Okay, the first thing is to migrate database to the containers such as Docker, because it can make it easier to run multiple MariaDB processes on the same host in different versions and configuration, and also better for resource isolation such as CPU or I/O. The second plan is upgrade MariaDB Server to 10.4 and 10.5. MariaDB has some more great features in 10.5, so that's why we're going to upgrade. Okay, the next step is to more automations. We have already made some automations as of now, but it's not enough. We're going to plan more, such as upgrading the base and restart the base. Okay, and also we are going to mix the base health report with tuning advice, with some tuning advice automatically. Okay. Okay, here is the base architecture at Bilibili. Basically, every cluster is running on 3 descenders for the purpose of business requirements and disaster recovery. And also we use single master, and other slaves are using GTI replications. So we have a system named Axel Server to perform database provision, switch over, replication, manage, and so on. And also we have database proxy for service traffic forward, database topology discovery, and read and write traffic split, connection port, and SQL blacklist. A proxy is set command and running with application containers. So by proxy, we can do something such as the database migration very easily. Okay. With the rapid development of business, DBA had to do more and more SQL reviews and execution tasks. So it may take a lot of time for DBA. And so we have automation system for some repeat tasks, such as hardware and database provision, and automatic database backup, and table structure audit, and data modification, execute safely, and online schema change. For online schema change, our system will use GHOST to perform online schema change automatically. And also, the system can provide the SQL tuning advice automatically. The developer can import the SQL, then he will get the tuning advice such as index tuning and so on. Also, we had made some automatic recovery from some failure. And for example, hardware crash, and the PCA SSD bug detection, and replication delay recovery, and it will downgrade the InnoDB, redo and bin log flash level for from 11 to 00, and so on. And also for the business traffic to some other slaves with no replication delay. And all of these are automatically. Okay. Here's the workflow for our self-service system. We had saved a lot of time by automation. Okay, scalp read. Export is very popular around young people, so there will be a lot of traffic during some export computation on live stream rooms. So, scale up reads mostly is very important for Bilibili. So, we use automation system to create a new instance and load data from backups and configure replication. Once it's ready, and we will perform some warm up, and the proxy will detect new slaves and make a reband for slaves. We can set some traffic forward with for every slave. Okay, finally, I will subscribe how do we make switch over. If we use some replication tools for switchover, such as MHA and so on, it will run the several seconds with service outage, because you need to set a master to be read-only and then wait the new master to catch up with replication. Okay, and so we are using a different way for switchover. The first step is to change the application topology from single master to master. the second step to reset global variables, automation increment and offset, aim to make automation auto increment for old master going to be odd numbers such as 1, 3, 5, and new master to be even numbers such as 2, 4, 6. Okay, so next step is to queue persistent connection on old master, then the product will handle the connection automatically. And the fourth step is to switch over and change replication for sleeves by automation system. The product will detect the new master automatically. Okay, and the fifth step is to perform the health check and then change the old master to be a slave and read only. The final step is to roll back the increments and offset to 1, 1 for global variables. Okay, that is how we perform switchover for production. So we are approaching to end of my talking, and thanks for your interest and attention.
I now have the pleasure to introduce you to the chairman of the MariaDB Foundation, Eric Herman, who will be talking about how to compare the ecosystems of MariaDB and the one of public code.
Hello. Today I'm going to be talking about comparing ecosystems, specifically comparing the ecosystems of MariaDB and public code. My name is Eric. I'm a developer and I have been for the majority of my career. My career has mostly been commercial, although I did work for MySQL from 2004 to 2009. But even during that time frame, a lot of the work that I did was on their commercial proprietary products. So even during that time frame, it was mostly commercial work that I did. That said, I am a long-time contributor to free and open source software projects. You will see commits in MariaDB, in MySQL, in the Perl interpreters, Perl core, as well as a handful of other maybe less marquee projects. I have been involved with the MariaDB ecosystem for a while. I've been serving on the board of directors since 2015. Currently, I am the chairman of the board of directors, so I'm serving in that role at present. Professionally, I work for the Foundation for Public Code as a code-based steward. In my role as a code-based steward at the Foundation for Public Code, I often point to MariaDB as an example, usually as an example to copy, a template that we should follow. But occasionally I talk about it as a counterexample. We don't want to do it like this. And so I'll definitely be highlighting some of that throughout the course of this talk. So first off, what is public code? Public code is the combination of software and public policy that is produced for and by the public. And as we think about it, software is becoming core infrastructure. We see cities collaborating in order to build the applications and services that are essential for them to execute their mission, whether that is allowing me to register for some form of taxation online, or it is for me to renew a permit, or schedule a big trash pickup, or anything. Many of the things that we expect to be managed by a municipality or by a larger public organization are now software. And very often public policy is being specifically implemented in software. So much like roads and water and waste disposal are all things that we expect public organizations to at least manage, if not run the detailed execution of, software is also becoming core infrastructure. The Foundation for Public Code publishes the draft standard for public code. This is a document which collects the set of requirements that all the software that we depend on as infrastructure should measure up to. Now, if you're a professional software developer and you read through the standard, I expect you will find very few surprises. I think that everything in there is going to read to you like the typical best practice, mostly what you're doing today. If, like me, you don't have a deep background in public software development, then the first time you come across some of the things that are a bit more policy related, that might be new for you. But other than that, I don't think you'll be very surprised. At the Foundation, when we look at a code base, we look at it from the dimensions of quality, community, product, and support. And quality is what I do as a developer. I work with the developers and we take a look at the standard, we compare their code base to the standard, and we say, does it have the quality we expect? But a code base is so much more than just the code, and even more than the code and the developers. There's many more individuals that make up that community, and so it's not good enough to just stop there. We must have a view which is wide enough to encompass all the different people that are either deploying, maintaining, monitoring, running the software, the end users of the software, the citizens for which this software serves. So the community can be much, much broader than the developers who are making the code and the managers. And like commercial software, we expect that there's more than just code sitting in a repository. We expect it to have what's needed to get it installed. We expect it to have what's needed to understand how to run it, that it has the documentation and the other things that a complete product has that not all open source projects have. And of course, you may not be in a position where you want to or where you're even able to install, deploy, maintain the code base yourself, and you may want to contract out those services. And so is there a support network that's able to provide you the help that you need so that you can do what you need to do? And so those are the four things that we look at. And in our organization, we don't do advocacy. What we do is we work with code bases to make sure that they are achieving their goals in regards to these four areas, but we don't have to convince them. They're working with us because they're already on this road. There's other organizations that do advocacy. The Free Software Foundation Europe jumps to my mind as their public money, public code campaign. But the organizations that we work with, they've already decided to work in the open doing public code. When I think about the mission of the MariaDB Foundation, they talk about different pillars. They talk about continuity, collaboration, and ecosystem, which I already see some overlap, but one of the things that stands out is I think that they are a little bit broader. And then there's, of course, the mission of the MariaDB Corporation, as well as all the other big contributors that contribute to the MariaDB codebase, as well as all of us as individuals. We don't even have a mission statement necessarily. We're users of the product. So when I'm comparing MariaDB to the standard, or when I'm comparing MariaDB to one of the code bases that I'm working with, there are times when MariaDB has an obvious advantage, and that is that MariaDB has a gigantic ecosystem. There's all the work that's coming from all the developers employed by the MariaDB Corporation, as well as the engineering coming in from the likes of IBM and Tencent and Alibaba and everybody else that has made very, very interesting contributions over the years. And the user community is very large indeed. So we wouldn't expect that if you are a city developing a license renewal website, that even if you are in collaboration with several other cities that have a similar need, that you're going to have nearly the user base of something like MariaDB. We wouldn't expect that you'd have nearly the developer pool of something like the MariaDB server. So it's not always a perfect comparison, and that's not even anybody's fault. That's just because sometimes there's not a match. But one thing that comes up is, are we developing a reusable component? Are we developing software that is more than just going to be used in this one project that can be used in other projects elsewhere? Is it going to have a life that is bigger than this one instance? And this is a great place where I get to compare with MariaDB, because in the case of MariaDB, users start with an application, maybe with a WordPress site. They don't think to themselves, I want a MariaDB database. They may not even think to themselves, I want an SQL database. However, MariaDB is a component that is a default in many Linux systems or other systems. So that's a great example that I can point to, and I used recently when talking about OpenZoc, which is a case management component. And if you're a city and you're developing something which is going to have a case management aspect to it, you don't start by saying, I want this specific case management software. You start by saying, I want to deliver a service. But maybe you're delivering that service according to the Common Ground standard, which is it's a way to write applications that was standard described in the Netherlands. And the OpenZac component fits into that Common Ground standard. And maybe OpenZac becomes the default in that standard. And then anybody developing a Common Ground app maybe will naturally reach to OpenZac as the first case management component that they would use. So that's an example where I get to draw a very close parallel. Another place that I get to draw a parallel is that, of course, collaboration comes with a cost. It there's, if nothing else, communication overhead in working with others. But I think about how MariaDB, the development started with one organization. Now we see development coming from many. Of course, there's the majority of development happening in the MariaDB Corporation, but we also see very interesting features coming from other places. And I think about the instant add column, which came from a brainstorm at MariaDB Unconference a couple of years back, and we had developers from Alibaba and MariaDB Corporation, naturally, and Tencent sitting together in a room talking about a way they could do this. And the prototype was actually developed by one of the Tencent developers. So that is something that benefits us all. And even though it was solving a very specific use case that they had, that's now something that benefits everybody. And so that's a great example and makes it parallel to one of the things that I see with the Signalen project, which started in Amsterdam, specific to their needs, and the Association of Netherlands Municipalities started working with Amsterdam in order to replicate that. And then, of course, they needed to change things so that it would be appropriate in some of these other contexts, in some of these other cities they wanted to deploy to. But those changes were also beneficial to Amsterdam. So yes, there's cost in collaboration, but then, of course, the obvious benefit is that the other developers are developing things that are not your highest priority, but you will benefit from. And the first thing that I do when I think about MariaDB and my role is I think about, so how does MariaDB measure up to the standard that we publish? Well, so does MariaDB code in the open? Well, the answer is yes. And when I'm talking to development organizations, especially ones that are just making the transition from working in private or behind closed doors anyway, working in a closed fashion, to wanting to transition to working in an open fashion, they are understandably hesitant about all of the things that can come up. And I get to point to MariaDB and I get to say, hey, they have their public development branches on GitHub. They don't just do a big release at version boundaries and say, here's all the changes since last version. Instead, you see the code unfolding as developers are working on it. And you know what? These developers make mistakes. It's fine. We're not going and pointing at them. We're not holding our bellies and laughing at the mistakes they're making. Instead, we understand that that's a normal part of the development cycle. We all make mistakes. Sometimes we make dumb mistakes. That's fine. They get discovered. We talk them through, and we come up with a solution which doesn't have that mistake embedded in it. And so that's something where, even though it's scary, we can see that these developers don't have to be afraid, because we can point to the MariaDB ecosystem and say, look at the work that's being done there. You don't see that there's really anything to be afraid of there. And it's not that all the code is perfect at all. And one of the things about working in this way is things that we might have been sloppy about, or it might have been just expedient to do something like put some secret data into the repository. Now we know that if we're going to publish this, we can't just, because it's easy or expedient, commit a password here. We have to have good hygiene, have our secrets in a separate location, not in the codebase repository. So there's a natural advantage that comes up that we want anyway. And then as we are working, if we're working in the open and somebody else is working on a long-lived branch or maybe a patch set, if we're working in this incremental fashion, it allows them to track our work again in an incremental fashion. And that allows us to work with a much, much wider range of vendors or contributors or individuals. And the standard talks about building reusable and portable and extensible code. And when I point to MariaDB, I get to say that these are aspects that have contributed to the fantastic success of MariaDB. No matter what operating system you're running, no matter what architecture you're running on, you can run MariaDB. But also, this is a bit of a counterexample because internally, MariaDB is not so modular. It's not so easy to reuse the bits and pieces. I'm not going to pull the parser out of MariaDB in order to examine the complexity or build a load balancer or something like that. So when I look for examples of systems that are internally well modularized and the pieces are reusable, I point to things like GNOME's glib, where projects that have nothing to do with GNOME are reusing bits and pieces of the glib libraries, or KDE frameworks, very much the same thing, where people who are writing things that aren't even intended to run on KDE are using some of the libraries that they developed to make writing KDE applications and writing KDE itself easier. And this lack of internal modularity is something that I think limits contributions, and I think that this is something that we as an organization, or as a community, as an ecosystem, I think this is something that we as an ecosystem, this is something that we should give some thought to. Is that a place we can improve? Something that's important for all open source code bases, whether public code or not, is that they welcome contributors. And if you are making the transition from developing in a closed fashion to developing in an open fashion, this is really hard. Part of why it's hard is that you probably don't have a lot of extra bandwidth for reviewing somebody else's contributions that are not in your highest priority things to do list. So you know that if you're working in the open, that you're going to have to invest in that. That takes a time commitment. And also, it's not a lot of fun to admit all of your mistakes in public, to have a public bug tracking system that anybody can look at and anybody can read and anybody can see. That's intimidating. And then we need to give serious thought to, okay, how is security issue reporting going to be? What's the right level of transparency for that? And then also, if we're making a public roadmap, which is important for encouraging contributions, because without a roadmap, it's very difficult for me to know whether or not I'm helping or whether I'm pulling the code base back in a direction it doesn't want to go. And so a publicly visible roadmap is useful to all contributors to know how their contribution slots in with the future as it may unfold. But a publicly visible roadmap also starts to feel like you're making promises, and you definitely need the freedom to be able to say, this is what I believe we're going to deliver, but this is not a promise of what we're going to deliver. And so articulating that well is important. So I think there's also room for improvement in the welcoming contribution of the MariaDB ecosystem. And specifically, what I detect is that there's a lot of undocumented tribal knowledge where all of us that are in the ecosystem have a sense of things that are not written down. For instance, one of the things I would like to do is I would like to get together with as many of the senior developers as I can get time with and get them to tell me what they hope to see change in the structure and the architecture of the code base. And then if I collect all of this together, maybe I can present it back to everybody and say, hey, is this our technical roadmap? So maybe that'll happen this year if I can get together with enough people and carve out enough time for that. Related to that, if I'm doing development, where are the engineering guidelines? There's a little bit on style, but in terms of really how one should approach coding, what's the right level of abstraction? When do I use inheritance? When do I use composition? How much should I be programming in a stateless functional style? When is it okay to manipulate as much state as I want? These kind of engineering guidelines I don't think that we have these written down. This is something that each developer on the server or in each of the connectors, this is something that they know, but is not explicit. So I think we could document that. And also, I think that we've not been good about what our feature roadmaps are going to be. But even though we haven't been good about this, this is still an area where we do naturally share it. Every time I'm at a developer meeting in an unconference or similar, the developers are always sharing what their challenges are, what the things they want to implement are and why. And so there is some knowledge about what is coming on the roadmap. It's just not written down. And so we do share this with each other. We just don't share it in a way that is very easy for people who weren't in the room to be able to learn. And so I think that this is an example where it's perfectly fine, but we could improve. Believe it or not, there's a bunch of code out there running in the world that is delivering a lot of value that is not under a version control system, that has backups with dates and times or version numbers in the file names, but is not in version control. Fortunately, version control is becoming the norm, I think especially thanks to GitHub and GitLab and the others that have made it so easy for those of us, regardless of how technical or not we are, to participate in the forking, modifying, requesting merges, seeing our changes get merged. So I think that these online platforms have made us all better users of version control system. So that's really good. And obviously, MariaDB is up on GitHub. It uses Git. If we go back through the Git history, not only do we see everything since it was transferred into Git, but we can also see the old Bazaar commits as well as the BitKeeper commits that stretch all the way back to Y2K. So that's a good one. I think that's one where we can show that it stands the test of time. And another thing that I work with all code bases on is to ensure that every line of code is getting reviewed. Every contribution, even documentation, everything should have more than one brain review it. That there's the author, and there needs to be somebody that's taking a fresh look at it as well. Let's not have the habit, as convenient as it is, of having the developer write the code, test the code, commit the code, and deploy the code, and have no sounding board to give them the insight that they overlooked something obvious. So this is something with the MariaDB ecosystem that I see is basically true in practice, but we could do this a little bit better. Specifically, we could have protected branches or enforce it otherwise. And there's times when I see request for review happen when it doesn't happen in a timely fashion. So I think we could get better about our responses to that when somebody adds a pull request, although I really, really appreciate how much work that is. And hats off to the devs that are doing that review, and I do understand that you are each very, very busy. When I think about the reviews, another area that I think we can improve a bit is we typically review the code and the tests very closely, but we think of the documentation separate as an afterthought even. And so I would like to see us, when doing some code, to also conjoin that with, and this is the change that's needed in the documentation, so that it's a single unit. And that's a bit of a stretch for us, I think, but that is an area that I think other code bases do better. And there are standards that are relevant to the MariaDB code base, specifically the SQL standard, but also, depending on which connector you're using, maybe the ODBC or JDBC or one of the other standards. And so our reviews of these contributions, are they having somebody look at not only the code and the tests, but also, is this bringing us closer to the standard? Is this unrelated to a standard, or does this bring us further away from the standard? And so this is something that I think I think it's just a place we could improve. I don't think it's a big deal, but I think it is something that we are not making explicit today, even though I think it happens more or less as it needs to on an ad hoc basis. But I think we could be more deliberate about this. And the one thought I had on this is maybe a reviewer checklist would help. I don't know if it would or not, but possibly. And another thought I have is that we don't engage enough people in the review process. People who are not developers absolutely are good candidates for documentation because they will read it as a non-developer, which is fantastic. So let's engage in our ability to do documentation as well as code. There's a lot of code I can't contribute to, but maybe I can contribute to the documentation that is of what that code is doing. So I think that we can increase the pool of people involved in the review process. Now, obviously, if I'm only working on the documentation, I can only sign off on, yes, the documentation for this looks good. I have no idea if the code is well structured, but my part, the documentation looks good. Or, hey, I don't feel like the documentation explains something that makes sense to me. Maybe the code is great. So we have to be clear, if we're only reviewing part of it, what role we are taking on in our role as a reviewer. Continuous integration is something that is important for every code base, and fortunately, due to I think largely we can give credit to the online repository hosting services like GitHub and GitLab and such. Continuous integration is becoming the norm as well, and MariaDB has had continuous integration for a very long time. It's had BuildBot since before there was Travis integrations and such. And BuildBot is continuing to improve, but it could be faster. There's often a big delay between when a branch is pushed or a merge request is opened and when we see the results of BuildBot. So that's something that could be better. Also, sometimes tests fail and then they get rerun and they pass. So there's been some unstable tests historically. I understand that that there's significant effort right now to identify and resolve all of the unstable tests. Maybe that's done now. I don't know. But that's something that I think is something that needs attention continuously. Also, test coverage is something that we don't report in the MariaDB ecosystem. So it is possible to run test coverage utilities, but we don't currently. And as a reviewer, when I'm reviewing code, I want to be confident that the code doesn't break anything, and what I'm reviewing is the structure of the code, is the clarity of the code. I don't want to have to, as a reviewer, try to be a test engine in my own head, imagining every corner case and branch condition. I would very much like to have the test suite give me confidence that the code works, so I can focus on, is it well implemented? Many code bases are doing now is they're saying you can't merge to the main development branch unless all the tests pass. And that's something I would like to see us be able to enforce in the MariaDB server code base as well, which we don't today. Documentation is an area that I think we can all participate in. So please contribute. The Standard for Public Code says you should document your objectives. Well, that's something that I think we do a reasonable job at. I think we could be more explicit about that, especially around which versions of the SQL standard and especially around to what extent we expect this database to work as an upgrade path from another database or similar. Document your code. Again, I think that if you're a developer, you're already doing a pretty good job of this. Obviously, this is something that I think few of us would say the documentation across all of the server and all the connectors is as good as we'd like it to be. So I think that that as you're working on code, also take the time to contribute to the documentation there. Use plain English. This seems really basic, but remember that not everybody reading the code is necessarily going to be a native English speaker, and therefore the documentation, whether that's in the code or on the website or anywhere the documentation is, please do your best to write it as simply and as clearly as you can. And the goal for the documentation should be to communicate. We don't have to show off how poetic we are. So anyway, use plain English, please. And I would say on the whole we do pretty well here, although I think I would like to see the per version information improve a bit, because when I'm running a particular version of MariaDB, sometimes it's not as easy to figure out which features I have and don't have. So I think there's an area there where we could improve, and there's examples we can look at in other software where they have that same kind of thing. So I think we can look at others and learn from them as well. Code-based maturity. Hey, Code-based maturity is an area where MariaDB, I think, does very well. The version numbering makes sense. It's very clear to understand when something is a release candidate or when something is prime time. So that's really good. And also the change logs are always informative and are good to give me the update I need for what changed in this version. So overall, there's a bunch of areas that I would like us in the ecosystem to consider when I look at the MariaDB ecosystem and the MariaDB server code base especially, and I compare it to the draft standard that the Foundation for Public Code is publishing. I think there's some areas that this causes me to highlight as areas we can improve, and I've talked about them, especially around documentation, reviews relative to the various standards. Can we get some branch rigor? There's more we can do in terms of testing and roadmap. Let's get some engineering guidelines together. Maybe I can work on that. And obviously the internal modularity, I think that's the most difficult one. But with all of this, most of the time what I'm talking about is we can do it the way they do it over there in MariaDB. That's a community that is doing a lot of things really right. So thank you very much, and I understand we're going to have some question times now.
Our next presentation is by MariaDB Foundation's very own Vincenzo Ciorbaru. Long-term archival with MariaDB's S3 storage engine.
Hello everyone, my name is Vincenzo Ciorbaru. I hope everyone's having a great fest. Today I'm going to talk to you about the S3 storage engine, which is a way to archive data within MariaDB on an S3 service. So what does S3 stand for? Well, it stands for Simple Storage Servers, and it's a way to store files in the cloud. It uses the HTTP protocol, primitives such as get, put, or delete. And with these, you can send any file into S3. This makes it ideal for archival purposes, but it's not very good with lots of small files. Actually, the ideal file size is around 4 megabytes or so. And this is important because if you want to access your data, especially if it's spread out around small files, you're going to incur a lot of performance overhead, namely with the network transactions. So this sort of service is implemented by many different providers. The original specification came from Amazon with the goal of providing data with millisecond delay and cheaper storage overall, especially if you access your data less frequently. So that's the goal of the service. Let's see how we managed to do this with MariaDB. So MariaDB implements now a S3 storage engine, and it is a way to interact with an S3 storage backend. With one simple command, you can move your tables from a production or operational level storage engine like InnoDB into the archive version of S3. By doing this, you get them as read-only tables, but you can use them as any other select. The S3 storage engine is built on top of ARIA, and there is one key advantage to building it on top of ARIA, and that is that you benefit for free from all the optimizations that ARIA supports. And on top of that, it also works with partitioning. There are some specific optimizations for S3, such as compression and a very useful table discovery that lets you access the data from multiple servers at the same time. And to be able to reduce network latency, it also has its own dedicated page cache, which is configurable. So let's see how we can use the S3 storage engine. The goal when it was first designed was to make it really simple to use. And all you need to do is configure where the S3 provider is. So you need to provide the host name, the S3's region, in case it's a cloud-based with multiple regions. Then you need to tell it the bucket name. And finally, just provide the access key and secret key credentials that the S3 provider supplies for you. Once you start up MariaDB with these settings and the plugin enabled, all you have to do is pick whatever table that needs to be archived and change the storage engine to S3. Changing it to S3 means that all the data from your production table moves to the archive. And that's all you need to do. Now, it's important that you understand a little bit of how the storage engine works behind the scenes, because then you can more easily reason about the performance implications. So behind the scenes, we first tried to implement the S3 storage engine like by using the Amazon SDK. Unfortunately, it didn't really go, it didn't have the API necessary that we wanted to use, so we ended up writing our own. we have a small library called libmaria S3 that behind the scenes uses libxml and libcurl for the networking aspects and the parsing of results. And with this library, we have some logic on top of ARIA. Now, the way things are stored, and because it's built on top of ARIA, you're going to see some similarities. We store in S3 each block as a separate file. And blocks are the size of that's specified as a parameter, and it's usually 4 megs in size. Now the table definition still holds an FRM, and here you'll see, here's the example of some files that you can find on S3 once you've moved the table. So you're going to have the FRM, which stores some metadata about the table. You're going to have the first index block, it's going to be called ARIA, and then subsequent index and data blocks are found in separate paths, the index and data paths. The numbers here you see are prefixed with zeros. The number of blocks is not limited to 6 digits. You can have more. We just chose to prefix a few more zeros just for easier reading, assuming tables are maybe roughly around 4 gigs in size, 400 gigs actually. Now, with this in mind, let's think how we could do replication with S3. So the server can be configured in 2 ways. You can use the same S3 storage on both the primary and the replica, or different S3 storages. So if you're using different S3 storage, there's really nothing you need to do. Every action that happens on the primary server has to happen on the replica. So regular replication will work just fine. The problem with this one is that you end up storing your data twice, and especially for a already high availability backup service, you don't really need a backup of the backup in this case. So the more favorable system is the one with a shared S3 storage and multiple servers used as a replication chain. Now, the problem with this one is that the replica server needs to do things a bit differently. Some transformations need to happen, and these are that whenever you convert a table to S3, when the information gets to the secondary server, the table is already there. So all the secondary server has to do is to drop its own production level table. And then, thanks to table discovery, the S3 storage engine will find the table stored in S3. The reverse operation, where you're trying to move from S3 back to a operational data, the table has already moved by the time the replica sees the alter table command. So instead, the replica, all it needs to do is to drop the instance that it knows about of the S3 instance, and then it needs to recreate the table as the destination storage engine. Unfortunately, this means that the replica does not have the data yet. Luckily, the master will send all the rows to it, so it will just insert all the data via regular binary logging. Now, you need to keep in mind that MariaDB is by default configured to assume separate storage, which means that the 2 relevant switches, replicate alter as create select, defaults to on. This means that all the table's rows are logged into the binary log, and then the slave will ignore any updates that happen to S3 tables. Now, this is what you want when the storage is separate, but if it's shared, the S3 secondary server must make sure to ignore any updates to S3 tables because the updates are already there. And in case you are in this sort of configuration, you need to manually set your slave to ignore updates. All right, so that's about it for replication. Let's see some details of how we could make use of S3 in practice. Well, you need to take into account, like I've said before, that the speed of these tables depends on your internet connectivity. So there's no way that the first access can be faster than how long it takes for your internet to fetch the first block, the ARIA block from before. Follow-up accesses will hopefully have the blocks in the page cache, so they should not have to go over the wire to get your data. But just in case this is not enough, to speed it up, you can compress your data, and by compressing it with the compression algorithm equals zlib, a switch for the S3 engine, then the amount of data stored in S3 is just the size of the compressed block. So that's a gain there. And in case that is still not enough, you can choose to increase your page cache. That way you can store more blocks in memory, and you probably have to go less via the network. Now, because all of this is a network-based system, you need to keep an eye on network traffic. Usually, S3 providers will charge for your network traffic, which means that S3 tables are nowhere near suited for operational use. However, they're very good for analytics and also infrequently accessed data like backups or disaster recovery situations. By choosing to compress the S3 tables, you reduce both storage and network costs, but whenever you use the tables, you have to do some more computations internally, so you might be CPU bound in that case. Although it's probably not something you should worry about, just something to keep in mind. All right, enough talk about features. Let's see how this storage engine works in practice. Let's open up a terminal and see how we can make use of S3. All right, we're at the terminal here. So what I have here is I am running a MariaDB 10.5 server. So we can check this out real quickly. And I have the storage engine plugin enabled, and we can check that out by looking at information schema. So information schema plugins where plugin name like S3. And to get a nicer look, notice I have S3, it is active. The plugin maturity is still alpha, so there might be bugs. However, it is still very much usable. So let's see how we can use it. Before we put a table into S3, first of all, let's have a look at what configuration file I'm running. So the key here is that I've set the S3 access keys as well as specified the bucket and the region. I don't need to specify the host name because by default it is going to be using Amazon. And I have my data set up in Amazon for now. Let's go back to the server and let's have a look at our database. So employees, we have a few tables here. It's taking a bit longer because it's doing engine discovery. We don't have any S3 tables inside, stored inside S3 yet, so nothing's been discovered. However, the biggest table here is salaries. So show create table salaries. We see it's still running InnoDB at this point. And what this table stores is what salary a current employee via the employee number has had from a specific date to another specific date. And we want to put this table into S3. And we can do this by just doing alter table salaries engine equals S3. Now this salaries table takes a while to upload to S3. So whilst it's uploading, let's talk a bit about the database. So I got this database from Giuseppe Macchia's GitHub repository. You feel free to try it out. It's a very good test case for prototyping because it's not a very small database, but it's not a very big one either. So it's good enough to try out different things. And here I have my S3 management console. Let's see if the table has finished uploading. So let's have a look in the terminal. And yep, we see that it's finished uploading in 24 seconds. Let's refresh our S3 interface. So I'm going to do a refresh. So loading, we see we have our database name here as a folder. Inside it we have salaries, which is the table we just dropped into S3, and then we have the FRM, we have the ARIA first block, and then we have data and index folders. If we look at data, here are our data blocks, each with the block size of 4 megabytes, and the final one is just not full enough yet. And likewise, we have for the index blocks, we have a bunch of index blocks. So far so good. Now let's try and use this table like we would normally. So back to the terminal. Let's figure out what the average salary is. Actually, no, let's get the minimum salary first. And this is the first time I'm running a query. So the first time I'm running it, it has to go all the way to S3 and back. So it's getting all the data, putting it inside the page cache, and then it's computing my minimum salary. So we got it. We see it takes around 14 seconds. But now, what if I want to get also the maximum salary for employees? I'm just going to do a max. And behold, it only took 0.7 seconds to get me the result. So this time it didn't even touch the network because we had all we needed inside the buffer pool. Of course, it did have to check the network slightly, so that's why we have a little bit of delay compared to a local table. But it's still much faster. We can also do complex operations with this table. Now, what if we want to get the average salary for each employee? Well, we can do the average salary from salaries, and we can group by employee number. But I want the average of these numbers, because this is going to be the average salary that each employee had. So I want to do an average from the result here, and I'm going to turn this one into a derived table like so. So what I'm doing here, I'm computing the average salary per employee, and then I'm taking the average out of all of these. And let's see how long this takes. 2.8 seconds. So we did have to do more computation, but we still didn't go all the way to network like we did here, where it took 14 seconds. So this is what makes the S3 storage engine good. It optimizes network traffic. And if we run it again, roughly same performance, which means that everything we had was in the buffer cache. All right, the final thing I want to do is, let's see if we can insert data into this table. So first of all, show create table salaries, and I'm going to try to run an insert into salaries values. Let's pick a random number, 5. The salary is going to be 30,000. The date is going to be, let's say, 2020 10 10, and due date is going to be 2020 10 11. And notice that the table is marked as read-only, so you cannot add data inside salaries once you've moved it to S3. You'd have to move it back to InnoDB or some other table, other operational table engine, and only then can you add values to S3. All in all, the S3 search engine is still relatively easy to use. Just make sure you get your credentials right, and you should have no problems afterwards. All right, I think this showcases the power of S3 in a few simple steps. Let's go back to the final slides. All right, now you've seen how S3 can be used. I need to point out some limitations before we wrap up. So notice that because of the configuration system, there's only one S3 key per server, per MariaDB server. That means that you can't access multiple S3 providers from one MariaDB. There are plans to eliminate this limitation by storing the keys inside the MySQL servers. That's probably for another development. Now, replicas on their own should make sure to not access S3 tables while the alter table command is running. Now, the reason for this is that there is no atomic transaction within S3, which means that trying to access tables whilst they're being uploaded to the cloud, you'd end up with some very strange results. Luckily, once the alter command is done, the replicas will be able to find the tables thanks to table discovery. And I did mention that S3 supports partitions. It does support partitions, but there are limitations. Operations like rebuild, truncate, or reorganize are not supported in S3. That is a debate if we should try to lift those limitations, but do let us know. And as I've mentioned, the minimum time for the first select is dependent on the S3 block size. So if that is a problem, you can try to reduce the block size. But keep in mind that we've already tuned S3 for optimum performance according to S3 specs. So reducing block size can lead to faster queries, but it can reduce throughput overall. So make your choices according to your infrastructure. That's it. Thanks so much for listening, and I will be ready to answer any questions you might have. Thanks.
And now we will have an optimizer trace walkthrough by Sergey Petrunya of MariaDB Corporation.
My name is Sergey Petrunya, and this is the optimizer trace walkthrough. Today we'll cover everything about the optimizer trace. So, optimizer trace, it's actually not a new feature. The initial prototype existed before MariaDB existed. It was initially released in MySQL 5.6, and the first release in MariaDB was 10.4 last year. After that we have added more tracing, got some experience of using it, so I think now it would be a good time to look at what optimizer trace and how we can use it. So before we discuss the specifics, let's discuss the goals. The goal of the optimizer trace is to show in details about what goes on in the optimizer. Typically the workflow goes like this. We get the SQL statement, it is optimized, then one can see the query plan if explained, then it is executed, and analyze for statements feature can be used to get information about that. But the optimization process has been fairly opaque, and now optimizer trace is used to provide details about what goes on here. And there is a lot. There are query writes, values, for example, view merging. There is very close analysis, search for query plan, finally query plan refinement. So if you have details about what goes on there, it allows you to answer questions. The most typical question is like why certain query plan is not chosen. If you have added an index and it's not being used, without optimizer trace, it can be very hard to answer the question about why is this index not used. The second very common use case is why are query plans different across database instances. This is a fairly common question where somebody is upgrading from one database version to the other, or is just setting up another instance, and it has of course slightly different statistics because statistics depends on the data layout, or there are some minor DDL changes. It's like a column has now different collation. It was nullable and now it's not null, or vice versa. And these changes seem irrelevant, but one cannot tell with 100% certainty. And without optimizer trace, one had to just manually inspect all of the parts of the environment and try to guess why the query plans are different. While with the trace, you can just get trace on the old instance, trace on the new instance, and then see what the difference is. And this is much more efficient. Finally, the trace makes it easy to ask for help or report an issue to the development team. Because having an optimizer issue and query optimization issue while uploading your whole data set is not always possible. It can be too large, or it can contain some sensitive data. Typically you can provide explain or table definitions, but these are not always sufficient. While the trace is of reasonable size, it is also a text document, so you can view it and remove any sensitive information from it, and then submit it asking for help, or even if you think it's a bug and optimizer, reporting it to the development team. So let's look at how one uses the optimizer trace. How does one get the optimizer trace? This is fairly easy. You just set this optimizer trace to 1, which enables saving the traces. Then you run your query. And after that, you do select star from information scheme optimizer trace, and one of the columns you get is the trace, which is a really long document with the trace. The traces are stored in memory. You can view only the trace for your session and only one last trace stored. So you need to do select star from optimizer trace immediately after your query. A query can be select it's typically better to use explain, and pretty much any statement that can have a query plan. So optimize your trace contents. It is a huge JSON document. Basic idea is that it's a log of all actions done by the optimizer. Now, I would like to say all actions and that you can see everything that optimizer did to your query, but unfortunately this isn't the case. The optimizer does a lot of things and not everything is traced yet. But I think we have a good subset of all actions, so all of important or typically like relevant actions are already printed, but don't expect to be it to be 100% description of what is your query. So why is it JSON? Well, JSON has two properties. First, it's human readable. It's easy to extend, so we can add more tracing as we go. The second is that machine readable. By that I mean that you can use JSON processing function to extract part of the trace. The most important one is JSON extract, which gets the JSON document as the first argument, and then you can give it a JSON path expression to what you are interested in. And the output of JSON extract is JSON document, which we can pass to JSON detailed, which will print the JSON. So this way you can get a piece of optimizer trace, and optimizer trace is typically quite large. So it's quite useful to be able to get a small subset of it, and you don't need to resort to some crazy regrep with grep. In case somebody are not familiar or don't have a clear idea what JSON is, here is one slide about JSON. JSON is a very simple simple language. Basically everything in JSON is value. A value is string in quotes, number, true, false, null. It can also be an object or an array. So array is input in square brackets, and it is a comma separated list of values. Now, values do not have to be of the same type. There is no data types, so you can start an array with string, then continue with number, then add a nested array, an object, and so forth. Members of the object is similar to array, but in the object the members are named. Here there's the first object with name, and then again the value, which can be anything, and so on. Typically the names of different members and objects do not overlap, and this is the case for the trace. Okay, so let's look at what is trace contents and how to interpret. Before we do that, some generic background information on query processing and SQL databases. It starts with an SQL statement, then there is a process called parsing, after which there is a parse tree, which is basically what comes into your mind when you look at the query yourself. Then there is a process called name resolution, which finds for each reference to table or view, which finds which table in the database it is. So what is the column names, what are the column data types. So if you have column 1 equals column 2, which data type would be used for perform the comparison, and so forth. So this parse tree with resolved names, there is no established name for it. Let's call it parsed query. Then there is query optimization, which comes up with a plan to execute the query. You get the query plan as a result, and then you execute. So optimizer trace is primarily targeted at query optimization, but it covers a bit of name resolution because some optimizations, some rewrites were traditionally done in MySQL and MariaDB early there. They're not large, but still you will see some name resolution parts. And for the same reason, it covers a bit of execution, although it's mostly in MySQL version of optimizer trace, not in MariaDB. But still, what you can see in the trace, you will see for name resolution, you will see join preparation member, which lists things which are basically done at name resolution phase. And one other thing that is not done is that just first it prints the query. And then I think there is attempts to merge view, and some other initial rewrites can be found in there. And you can also see there is a select ID equals 1, so this is done for the top level select. Then join optimization. This is the biggest element typically, and there are a lot of things here. And finally, there is join execution element, which is generated when it is executed. As we see here, that this is all for select ID equals 1. This is because each select is optimized separately. Well, there are exceptions to that. The select can be merged to its parent select, it can be converted to semi-join, and so forth. And then for each select, the optimization phase is shown in the diagram. Although there is some exceptions, but the general workflow is that for each select, we first do rewrites and transformations. Then we collect table information and table statistics. This is like preparing for the game. Then there is a main game join order choice. This is like the hardest choices the optimizer has to make. After the game is done, there is some fix-ups and plan refinement where we fix all the details, and this is, in the end, we get the query plan. So in the trace, this looks like this: join optimization, select ID, then there's a steps, which is an array of objects, and there are different objects denoting different things. As you see, there is always an unnamed objects because object can't have names. Then there is a name and either object or array. So the important ones are ref optimizer key uses. This is generating ref access. Rows estimation, then again, this is also an array that for each table there is, we collect table information by estimating number of matching rows. The main game, the join optimizer choices in considered execution plans. And as a result, you get this best join order. And then there are some other fix-ups or plan refinement steps, depending on what is in your query. So let's look at these elements. Start with ref optimizer key uses. Ref optimizer, let's try a query. Select star from T1, T2, where T1 key column equals T2 key column. This will give us an explain. It has put T2 table first, then there is table T1, and it uses index lookup, it uses key column, and it uses ref access. So a question one can ask, could this use the other join order instead from T1 to T2? Here T1.keyColumn is an integer and T2.keyColumn is a varchar of 100 with UTF-8 general CI. If you look at the optimizer trace, we will see ref optimizer key uses. It is an array that has only one element, T1 key call, and the value for it is T2 call. And note that there is no other vice versa. So we can make lookups one way. Interesting, let's compare that with the other way. What if both columns were varchars? Let's, instead of table T1, use T3 and write the same query. And here we see that lookup is possible in two directions. There are two entries. Here there was, well, if you know the optimizer well enough, you can guess that if in integer is compared to string, then they are compared as double values, and comparison of integers, which is this index is using, is compatible with that, while comparison of doubles is not compatible, because basically 0, 0, 1 is the same as 1 when you compare them as integers, but if you compare them as strings, these strings of 1 and 0, 0, 1 can be very far apart in different parts of the index. Well, but with the trace, you don't need to remember all of these details. You can just see that, okay, here there is a way to look up in table T1 from T2, but not other way around. This again can be very looks basic and kind of obvious for these simple cases, but can get much less obvious for much more complex cases where there are complex where clauses and the optimizer makes certain inferences of them. And believe me, even for the query optimizer developers, it's not always apparent whether the optimizer was able to infer some equality or not. The second interesting part is range optimizer. Range optimizer is a part of the optimizer which looks at the where clause and infers which ranges we may scan to find matching rows. And this inference can get quite complex. The first source of complexity is multi-component keys. Then there are also inference using equalities. If call1 equals T2 and there is call1 less than 10, the optimizer will infer that call2 less than 10, well, in most cases. And the problem for all of that, explain format JSON will just show used key parts, how many key parts are used. So let's take an example. Here there is a table some events with start date and end date, and there's an index defined on start date and end date. And then there is a query, okay, I'm looking for events with start date greater than June 24 and the end date less than June 28. Like I want to catch an event sometime. And the explain will show you that two key parts are used. But you might be surprised at a very kind of sluggish performance, or the range access is not used at all. And if you look into the trace, you will see that surprisingly the second key part is only using null. Now the discussion of that is sort of outside the scope of this talk, but basically to be short, is that the optimizer is actually not aware that the end date must be greater than the start date, and if you let him know that by adding these conditions, here then you will see that the range being scanned is much more narrower, and there are a lot fewer rows in it. Another example with multiple ranges. Now let's write a query where start date is one of these 3 days and there is just one end date. We will see that actually it generated 3 ranges, each of them using 2 key parts. Well, so far it's okay, but for longer or bigger in statements, there are this cross product of taking all ranges for key part 1 and producing cross product with key part 2 can cause some undesired effect against. So sometimes it is useful to know how the optimizer was able to handle it, because it employs some aggressive techniques to reduce the number of ranges it is producing. Closely related to range optimizer is so-called loose index scan optimization. Loose index scan optimization is optimization used for group by queries. It can be quite useful. Loose index scan can be quite faster than other grouping strategies. The choice whether to use loose scan is cost-based, so it depends on the data statistics and also on the data from analyzed table. It also has quite complex applicability criteria. So let's take an example. Let's create a table T and create a key of 3 components. KP1, KP2, KP3, and let's set 2 very similar queries. We do group by of KP1 in both cases. Then we want to find the minimum of KP2, that is for each group. And then there is a where condition, in this case on just KP2, and here it's on KP2 and KP3 also. And explain will show that this query is using loose scan, while this one is not. And it's not at all clear why would that be so, until you look at the optimizer trace. And here you see that the loose index scan is used, and here it is not, and it's usable false, cause key part after infixing the query. So now we see that the problem is not data statistics, the problem is not analyzed, the problem is that in loose index scan is not usable here. Good. So let's get to the next part of it, join optimizer. Join optimizer is the biggest, most important part of the query optimization probably. And it produces two objects. One of them is considered execution path, and the second one is the best join order. Let's take a look at the example. Let's get a join. This is tables from DBT3 benchmark. There are parts which are produced by manufacturer. There are suppliers. And in the warehouse, you have parts that are available in the warehouse. And so we write a join with these join conditions, connecting part to part soup and part soup to supplier. And then there are also where conditions on manufacturer, on part manufacturer, on supplier's account balance. So we are looking at, we want to find parts from this manufacturer provided by the supplier from with negative balance, which we actually have in stock. And this is the explain. It shows the join order. Well, best join order will show us the join order as well. And considered execution plans object will contain a log of how the join optimizer has arrived at this query plan. Now it has a lot of content, so it's too much for the slides, or too much. It would be too much for the screen, so we would need to use grep. Join order is constructed in a top-down, that is first to last way, and there are two important member variables here. Plan prefix shows what is already constructed, and the table shows what we are trying to add. And the table always follows plan prefix. So if you just grep, if you just save the trace to the temporary file, and then we just grep for plan prefix and also ask it to print one row after the match. So this way we find that, okay, we started with empty plan prefix and added table supplier, then we added table parto, then we added table part soup. And this was, then we got back to the prefix of just table supplier, and added part soup, and added part after that. And this is, by the way, the join order that the optimizer eventually decided the best. But it didn't stop here, it also considered two other prefixes. It didn't, notice that here it didn't consider three table prefixes or full join orders. This is because the join optimizer aggressively prunes away. It tries to not to explore join prefixes which are not promising. And here we can actually already see which join orders, which prefixes were explored and which weren't. Let's look then at how join optimization proceeded for the join order here. So first, plan prefix is empty and the table supplier is first. If we search in the trace, we will find this one. Best access path is a function in MariaDB or MySQL source code which adds a table to the prefix. What it basically does, it considers various access types and it computes how many rows it will need to enumerate, what would be the cost, and then shows whether it's chosen or not. So here it chooses range access, which would produce this many rows. Yes, and it has chosen it. This is a rows for the number of output rows for the plan so far and the cost of it. Okay, so after the supplier, we get to part soup, prefix supplier, table part soup. That shows there are two ways actually to access it, ref access and full table scan. It picked ref access. And then there is a third one. Prefix is supplier part soup, and then we are adding table part. Again, there are two ways to read the table. We pick the ref access. And well, this is a good query plan without an issue, so we don't see any issues here. But in case you are wondering, is the optimizer considering to use certain index for this join order? Is it what estimates it's using? Here for the primary key, it's kind of obvious that there will be one match. For non-unique indexes, which have some conditions are constant and some conditions are not constant, the estimate here is computed with quite complicated computation, so it's interesting to see. If there is a where condition attached, the optimizer will try to estimate its selectivity and print it here, which this success rate of this, like say, varies a lot for not just for MariaDB. For this is a hard query optimization problem. So here, this is something the optimizer can get wrong. This is how it raise. Okay, so this is the third table part. So we know that how many rows the optimizer expected to see, what would be the cost, join output cardinality. Let's look at why didn't it pick the other way? We saw that it went from supplier to part soup to part. How about part to part soup to supplier? We start with table part. It would use this table scan. This is how many rows it will produce. This is the cost of it. Then let's see, table part soup is added. Then there are 3 ways to read it. It picks the best of them is ref axis on table. The best of them is ref axis, but it shows that it has been pruned by cost. Yeah, so this is how you can view the details. So join optimizer takeaway. Consider the execution path traces the join order choice. It can get very large, so you have to use grep for plan prefix. Best join order will show the final prefix. By the way, hardcore JSON path users might want to, instead of grep, use searches like JSON extract and then use a filter. Unfortunately, one can't do this because MariaDB's JSON path implementation doesn't support filter. Neither does MySQL's, by the way. So you'll have to use grep and get a good text editor to navigate this very large document. So things we've covered so far, we've covered ref axis, rows, part of rows estimation, join optimizer. Well, there is a lot more in the optimizer trace. There are rewrites, various rewrites and transformations like view, CT merging, into exist subquery rewrites, min-max transformation. Then at collect table statistics, there is it reads data from histograms and tries to estimate selectivity. It searches for constant tables. Some tables are marked as constant. It shows the trace shows that. Table elimination optimization eliminates some tables, and it shows that. Then there is a conditioned filtering optimization, which we will see what filters are applicable for which tables. Unfortunately, this is all outside of the scope of this talk, but I hope you're getting the general idea about what kind of content is one can find in the trace and how to make use of it. Now let's look at the optimizer trace in MySQL. Now I don't want to have some kind of a match about which one is better, but I'm a big believer that we should, if there is something related or something that we could draw ideas from, we should look at it and discuss which of the implementations is better and how we could benefit. So optimizer trace in MySQL is similar to MariaDB in both user interface and the trace structure and the elements you find in the trace. There are, of course, differences. First is that the optimizers are fairly different, so there are different things printed. Also, there are a slightly different set of things being traced. So while the traces will resemble each other, I don't think just running diff might be hard. And then the tracing module in MySQL has extra features. So let's review them and see if there is anything we could learn from MySQL's implementation. So the extras in MySQL, the first one is that it can capture multiple traces for nested statements. If a statement invokes another statement, which can be done with a stored procedure when statement uses MariaDB will only save the trace for the top level statement, while in MySQL it will actually save the traces for substatements as well. This is controlled with optimizer trace of set and limit. So you can set it to save first or last n traces produced inside the statement. But the issue here is that basically there is no other support for troubleshooting nested statement. For example, you can't get explain output for this substatement. You can't get the statement time, how much time the statement has executed. Well, in some cases, you can infer the statement time and even number of rows examined from performance schema tables, but this only works if your stored procedure is very simple and doesn't have any complex logic. Because if it does, it doesn't show you the statement text, so it will be really hard to figure out which statement it has in mind. So my takeaway is that I don't think this is useful in this current shape. If you have optimizer problem inside stored procedure, the practical way would be to take away that statement out of stored procedure and troubleshoot it separately. The second extra feature in MySQL, one can omit parts of the trace. They have optimizer trace features variable, which is a set of flags: greedy search on off, range optimizer on off. These you probably recognize. Dynamic range on off, repeated subselect. So you can switch these off and then the trace will not be saved for those. Well, my answer to that why would you want to turn them? It's not an issue. The issue is not with the trace sizes as such. The issue is that we want to look at only particular parts of the trace, and typical workflow would be to use JSON extract to get the part of you need, rather than using flags to chop off the parts that you don't need. I agree that the flags would be useful for some global settings, like let's print cost values or don't print cost values if you don't care about cost values, which apply to all elements in the trace everywhere. In other words, I don't consider this. This is something we could add, but I don't think it's very important or very needed. Yet another extra is in MySQL, one can control the way JSON output is formatted. The first thing is that you can set one line flag to on in the optimizer trace variable itself, and in that case you will get trace in one line, which will probably make it take less space, but again, I personally never saw any need for it. The other one is that you can set, there's a variable called young markers in JSON. If you set it to true or on, you will have these young markers, so steps. When the array ends, you will have this comment indicating that this is steps ended, and so forth. Well, this improves readability somewhat, so somebody might find this useful. My issue with this is that JSON actually doesn't allow comments. So if you set this on, the output is not a valid JSON anymore. You can't pass it to JSON extract, for example. And maybe this should not belong to some global variable which suddenly makes JSON something non-JSON, but rather a function which prints it. It would also add something to make it more readable. Yet another extra is that tracing in MySQL covers some parts of the query execution. Most notable users file sort. For example, if you want to know whether file sort is using priority queue optimization, this is not shown in explain. You can only get it into if you enable the trace and run the select, not explain, but select itself. This also shows like a memory available and other details. And well, my guess is that MySQL had to put it somewhere. They couldn't put it in explain for technical reasons, and they didn't have explain analyze back then, so they had it save it in the trace. This is actually not a very good idea, because if the file sort is done in subquery, this will produce loads of repetitive JSON, and that's why they needed to disable it here. in repeated subselect to avoid producing really large JSON documents. Well, in MariaDB, this kind of information is shown in analyzed format JSON output, which is the command specifically targeted at collecting runtime statistics. So we don't have and don't think we should have this in the optimizer trace. Analyzed format JSON shows roughly the same information. Okay, so that's for extras in MySQL. What's extra in MariaDB? You may ask. Well, in one word, just I would say more polish. We were trying hard to eat our own dog food and use trace for performance troubleshooting we do. So things that we did, we made printout of conditions more readable. Here's how condition looks in MySQL, and here's how it looks. The same condition looks in MariaDB. This may not look like a big thing, but this amount of ridiculous overquoting makes conditions really hard to read, especially when the query is large and conditions are long. Well, we saw that data constants are printed as hex, not dates. We fixed that. The important thing did other similar smaller fixes. The important thing is that MySQL actually prints incorrect for range analysis for multiple key parts. We had a similar problem. We made the similar mistake in MariaDB, but we had caught it and fixed it before we released. Here is a bug in MySQL which shows that when I reported it to them, they didn't seem to care. So conclusions. Optimizer trace is available in MariaDB. It shows details about query optimization. You can analyze it yourself, or you can save it and submit traces when discussing or reporting the optimizer issues you encountered. MySQL has a similar feature that has some extras compared to MariaDB, but they don't seem to be important. Our future plans mostly is about printing more useful information in the trace. We want to we don't want to print everything there to flood it with content. It's already quite large, but we want to use our experience to find what would be useful and add printouts for that. So submit us, if you encounter optimizer issues, submit them to us together with traces, please. So that's it. Thanks for your attention.
So that was it for today's MariaDB Server Fest 2020. I'd like to say see you again tomorrow at the same time in the same channel, but it won't be the same channel. Stay tuned at mariadb.org/fest2020 and you'll see the channel to attend tomorrow. See you then!